Hello, everyone, and welcome back to another edition of the GammaRay Report. My name is Rose GammaRay. I'm an aerospace engineering professional, lifelong science enthusiast, and complete space nerd. And my goal on this channel is simple, and it's to take fascinating science and explain it in a way that's accessible, engaging, and hopefully makes you look at the world and the universe a little bit differently. So, right now, as you're sitting here and watching this live stream, believe it or not, but Earth is actually protecting you with an invisible force field. And if that force field suddenly disappeared, life on Earth could look very different. And in fact, that invisible shield may be one of the reasons that life on Earth has survived for as long as it has. But this raises some pretty incredible questions, such as what exactly is Earth's magnetic field and why does our planet have one? And what is it actually protecting us from? And perhaps most importantly, what would happen if Earth's magnetic field actually disappeared? And so tonight we're going to answer some of those questions, starting with something very simple, and it's essentially talking about magnets. Because it turns out that if you start thinking about how magnets actually work, you end up talking about some complicated things such as quantum mechanics, solar storms, the fate of Mars, and all of these kind of lead to the reasons we're all here today. But before we get into any of that, I would like to introduce my very special and one-of-a-kind co-host for tonight, Goldie GammaRay. Hi, Goldie. Welcome.
Hi, Rose. Hello. Hi. Great to be here.
How are you? How have you been?
I've been good. I've been good. Took some time off to, deal with a few things, but guys, I missed you all and I'm really excited to be back. Going to be going back to Iran Revolution Live and the Goldie Show starting tomorrow. I am so excited. I can't wait. There are so many updates, so many updates. But as always, I just want to say hashtag Goldie is always right. And I think the events of the last week have shown that. But that's for tomorrow's live stream. Right now, I'm so excited to be here learning about magnets. Like, it's just such a, well, I mean, it's one of those things that is just like we use magnets in so many things, but we don't really understand how it all works. And so I'm really interested to understand the science behind it, because when you think about it, Rose, it's almost like magical in a way, like the way magnets work. Like, how does a compass know to always point north based on like magnets or something, right?
Yeah, that's a great
So
question, Goldie. Is it magic? I don't know. What is this force field? Is it, it kind of sounds like it could be from Star Wars. It sounds like it could be from Hogwarts, or it's just the laws of physics and nature. Maybe a bit of all of the above.
maybe. So
But it's so nice to see you again, and I'm really excited for your show. So we were talking a bit before, but I've actually been having withdrawals. Um,
oh
I,
no.
I was so used to watching your show every day for like 100. I don't even know what we are, like 190, 180, who knows, something insanely high. And so I'm really excited for that starting tomorrow. So that's exciting. But yeah, tonight Goldie is all about magnets. And yeah, let's just get into it, because if you do think about it, magnets are a little weird, right? Like, we all kind of grew up with magnets. We all have been playing with them in some shape or form. So, they've kind of always been around. But because of that, it's possible that a lot of people haven't actually stopped to kind of question them or think about what's actually happening there, and what's actually working. So I do have some toys tonight to kind of show. Um, so I have some magnets, and we're going to try to do some live demos. So this is an example. Sorry, let me try to get the camera to focus on it. Can you see that?
Kind of.
Okay. Well, this is a magnet. This is another magnet. And they both have, each magnet has a north pole and a south pole. And basically, opposites attract and like sides repel. And so I will show you what that could potentially look like. Hopefully this works. Please bear with me. So we have our trusty National Geographic as a base. This, guys, is the May 2026 edition. And we have this one magnet that has wheels. So it has a north side, which is the red, and the south side, which is the blue. And so I'm going to place it on this trusty base. And then we got our other magnet. So the blue is supposed to repel, and the red is supposed to attract. So we're going to try the red first. Okay.
Magic.
I don't know. Okay, let me try that one more time because I don't know if the angle was right. Okay, one more time. So it's moving towards it. Oh!
I saw that.
We're going to try repelling now. So the blue and the blue are both south poles. So we're going to repel this now. And I actually have a little bit stronger of a magnet here that I got from Dad. Thank you, Bubba. So let's see if this does a better job at attracting.
I agree. She's a witch. What is this witchcraft?
Okay, so general idea. I mean, if you've never played with a magnet, that's kind of how it works. Live demo, guys. We're very, very high tech on the GammaRay Report.
Gartnus makes a really good comment. Science is basically real life magic. Like if you understand it, yeah,
absolutely. And then I also have, so this is a cool toy that I got a while ago. It's basically an hourglass, and it's made up of iron filings. And so there's a magnet at the bottom. So if you can see, it's got like a cool little shape here. And then if you twist it, so the magnet is making it form into like this cool little shape. And that's, again, because of the magnetism there. And then I'm going to just try to see if I place this magnet. So you can see it. I don't know if you can see that. It's like kind of pulling the iron filings away.
Oh, yeah. Okay.
Yeah. So it's kind of like interrupting.
It's pulling it towards the magnet.
Exactly. Yeah. So it's pulling it away from like the bottom and pulling it towards that magnet. Because again, those are some iron filings, and just shows some of the magic of magnets. Pretty cool, right?
Yeah.
Magnets work, guys.
Wow. So you know what? There's a really good question here, and I'm hoping that I guess maybe like throughout the live stream, like we'll get the answer to this. But Billy Cunningham is asking, I've never fully understood what is positive or negative about a positive / negative electric charge.
Yeah, we'll definitely get into that.
Okay.
Yes, thank you so much for the question, and keep the questions coming, guys. We'll try to get through as many as we can in the actual content of the show, and anything that we don't happen to get through, please definitely keep them coming, and we'll try to address those. But essentially, when it comes to magnets, you really have a piece of metal that's pulling on another piece of metal without touching it. So as you guys saw, live demonstration, there was nothing visible connecting any of the metal together. And you also saw that it could repel another metal as well. So the exact same physics that are happening inside of a magnet is also happening within the entire Earth as a whole. So in essence, a high level definition of a magnet is an object that produces a magnetic field. And I understand that that's kind of using the definition of like the word within the definition. And I'm going to go over a little bit more on what that means. But basically a magnetic field is the area around the magnet where the magnetic force is operating. And so we actually, to understand this a little bit more, we have to go a little bit more in depth into the physics behind it, and specifically around quantum mechanics, because some of this is working at like an elementary particle level. So we got our first diagram of the night, which is the fundamental forces. So we have 4 fundamental forces in the universe, and basically they essentially govern all of the interactions that we see within the universe. And so the first one is one that I'm sure you guys all are familiar with. It's gravity. Let me just adjust this a little bit. Okay. So gravity is likely the force that most people are familiar with, and it's responsible for keeping us on the ground. It's holding the Earth in its orbit around the sun. And according to Einstein's theory of general relativity, gravity isn't really a force that's pulling objects together in the traditional sense. Instead, it's that you have these massive objects that are warping the fabric of space and time itself, creating these curves, and other objects kind of follow the shape of that curve. So if you can see in the diagram, you can see the Earth is kind of warping the fabric of space-time, and that's essentially, according to the theory of general relativity, is what kind of addresses gravity and affects the motion of galaxies, stars, planets, and even things like light. So anything in our universe with a mass has the ability to make its own dent in space-time, creating objects to be attracted to one another. So Goldie, you have your own dent in space-time as well. So do I, and everything really. Gravity, however, weakens very quickly with distance. So, for example, if you double the distance between 2 objects, the gravitational pull doesn't actually get cut in half, but it becomes 4 times weaker. And if you triple the distance, the force becomes 9 times weaker, and so on. So gravity's major advantage, however, is that it acts over enormous distances and is therefore responsible for shaping very, very large scale structures of the universe. However,
that kind of reminds me of your live stream about the sun, and how, like because of the mass of the sun, and it was pulling things in, and then particles were taking more time to get out, and that's why like the sun is dying, because of like the gravitational pull versus the density and all that stuff, right? Kind of reminds me of that.
Yeah, it's definitely pulling on some of the same concepts for sure. But the gravity itself, out of the 4 fundamental forces, is actually the weakest one. Next up, we have the electromagnetic force, and this is the one we're going to focus on tonight, but I will be briefly covering all 4. Just because
I feel like you're explaining like the Avengers or like the Fantastic Four. It's like, the 4 forces of the universe, and like each one is like a superhero character or something.
That's so funny. There was a movie called Fantastic Four, right? So maybe this is like a different version of the Fantastic Four. But yeah, so next up we have the electromagnetic force, which is going to be the highlight of tonight's show. But this is essentially responsible for things like electricity, light, chemistry, and magnetism. And unlike gravity, which acts on anything that has a mass, the electromagnetic force only acts on particles that have an electric charge. And so one of the really interesting things about electromagnetism is that it can both attract and repel, as we saw with the magnets. And positive charges repel other positive charges, negative charges repel other negative charges, but both opposite charges attract each other. So negative and positives attract one another. And this actually turns out to be responsible for a huge amount of what is actually happening in the universe. For example, every atom that you've ever heard of exists because of the electromagnetic force. And this kind of goes back to some previous episodes as well, where we talked about what an atom looks like. And so an atom consists of a positively charged nucleus that's surrounded by negatively charged electrons. And the electrons don't simply fly away because they're attracted to the positive charge of the nucleus through the electromagnetic force. And it doesn't stop there for the electromagnetic force. Any sort of chemical bond, molecules, literally anything around you is existing because of electromagnetic interactions. And even the atoms in your body and the atoms in the chair I'm sitting in right now are all surrounded by these clouds of negatively charged electrons, and those electrons strongly repel each other through the electromagnetic force. So what's interesting, and this is interesting to think about, is that what you experience as a solid piece of matter is in fact the electromagnetic force preventing atoms from occupying the same space. So electricity and magnetism are essentially two different aspects of the same fundamental force. And we're going to go more detail into that, but that's essentially electromagnetism in a nutshell. And then next up, we have the strong nuclear force. So we've also talked about this previously. This is the other piece that is essential for the atom and is literally the force that is holding matter together. And without this, atoms also couldn't exist, meaning you need this as an essential force for anything in the universe to exist. I believe we went over this in the uranium enrichment episode a couple of weeks back, but essentially at the center of every atom is a tiny, incredibly dense region called the nucleus. And it contains protons and neutrons, and together those two things are called nucleons. And the problem here is that protons all carry a positive electric charge. And according to electromagnetism, positive charges repel each other because they're the same charge. And so the reason that the nucleus doesn't just explode apart is because of the strong nuclear force. So the strong nuclear force in tandem with the electromagnetic force is what is keeping an atom in balance and is keeping it together. And at the scale of the atomic nucleus, the strong force acts like this incredibly powerful glue, and it's overwhelming the electrical repulsion between the protons and binds the protons and the neutrons together. There's definitely a lot more that goes into this, especially when you consider things like quarks, which are even smaller particles that make up protons and neutrons. And we could really have like a whole live stream on subatomic particles and quantum physics and all of that. But essentially, these are all held together by the strong nuclear force, which is carried out by a particle called gluons. And then finally, you have the weak nuclear force, which is responsible for some of the interactions between some atomic particles that make up matter, including the quarks that are inside protons and neutrons. So, well, the quarks are what, like even more elementary particles that make up protons and neutrons. And essentially what's unique about this is that it can actually change one type of particle to another. So it does this by changing one type of quark into another type of quark. So protons and neutrons are made up of combinations of quarks, including up quarks and down quarks. And the weak force has the ability to actually transform up quarks to down quarks and vice versa. So for example, if one down quark inside of a neutron changes into an up quark, the neutron suddenly has the quark makeup of a proton. So it actually converts a neutron to a proton. and vice versa. And so this literally means that the weak nuclear force can literally change one type of matter into another. And so again, like we can go really in depth into this, but many things like radioactive elements are radioactive specifically because of the weak nuclear force. And so when an unstable atom loses, when an unstable atom's nucleus loses energy, it releases some of that radiation and it sheds a particle and becomes a more stable new element or a different isotope of the same element. So that's as much as I'm going to explain about these forces. And again, like we can go really in depth into all of these different kinds of subatomic particles and what they mean. It's not easy.
I think it would be cool if you did like sorry,
like a quantum mechanics subatomic particle.
I was getting some feedback.
Oh, is it better now?
No. So, well, sometimes it does this. So, wait, I think it's better now. Okay, I don't know what that was, but I was gonna say I think it would be really cool if you did like a short, like a 4-part video series where like in each video you kind of do like a 10-minute breakdown and explanation of like each electromagnetic force. It could be like a small science mini series. I think that would be kind of cool if you did something like that.
Yeah. Do you mean like each of the 4 fundamental forces?
Yeah. Each of these 4 forces, like, if you did like a 4-part, mini series, 10 minutes on each one explaining it, I think that would be kind of cool.
Yeah, that'll actually be interesting because like I don't know if I could do like number 3 and 4 justice by giving each one 10 minutes, but I think that'll be a challenge in and of itself to see if I can do something like that. But yeah, that's definitely interesting because
I think it would be helpful, especially maybe for people like in high school who are like maybe cramming for an exam last minute and they want like, a 10-minute video on, okay, what do I need to know about like strong nuclear force in 10 minutes before my exam, right? Like a course notes version of things. I think that would be kind of cool if you did something like that.
Yeah, okay. I will definitely add that to the list. But yeah, so that is the 4 fundamental forces in a nutshell. And going back to magnetism. So at this point, we've established that magnetism is a part of electromagnetism, which is one of the 4 fundamental interactions within the universe. And so the real question now becomes, where does the magnetism actually come from? Why is a magnet magnetic? And Gold, did you have any guesses?
Magic.
Yes, you got it. No, but really, so the answer comes down to electrons, specifically the quantum mechanical properties of electrons. So sorry, guys, we're not out of the weeds yet as it comes to quantum mechanics. We're going to have to go back a little bit more just to understand the actual mechanics of what creates magnetism. So I'm going to share my next chart here. Share screen. Okay, so I want to remind us a little bit about what atoms actually look like. So this should be review, guys, hopefully. Unless it's your first time here, and if it is, welcome to the GammaRay Report. Okay, so going back to, oh my God, Goldie, you know what I forgot to do? Oh no.
Oh
no. Okay, sorry guys. It's not too late. It's not too late. Put on your seatbelts and get your permission slips out, because we are jumping on our Q400 plane and taking a ride to Where are we going, guys?
Magnet land.
Magnet land. We're going to Magnet land. Yeah, so this is my Q400, guys. It's the plane that I worked on as an aerospace engineering professional, and it's my favorite little guy. So yeah, okay. Oh, I can't believe I forgot that.
That's okay. I've forgotten things during my live stream too, but hey,
All good.
you remembered. All good. So
Okay. So
oh wait, I did.
perfect.
Wait,
Okay.
wait.
So going back to what an atom looks like. So every atom contains your positively charged protons, your neutral neutrons, meaning they don't have any charge, and then your negatively charged electrons. So when it comes to magnetism, historically, scientists actually thought that magnetism came from electrons literally spinning around like tiny planets. However, that's actually not correct, and we're going to get into that a little bit. But essentially, if you've ever taken any sort of introductory physics courses or any sort of science in high school, you might remember that moving electric charges produce a magnetic field. So the logic here from the scientists was that electrons are charged negatively, they move, and so therefore electrons are creating magnetic fields. And that's partly true, but then quantum mechanics came along and actually made things a little bit more weird, because that's what quantum mechanics loves to do, guys. It just loves to make things weird. So physicists discovered that electrons actually have this property called spin. And so I need to emphasize something here, because the name spin is actually a little bit misleading, because the electrons are not literally spinning. So there was an experiment where if you tried to calculate how fast a tiny electron actually would need to spin to produce its observed magnetic field, parts of its surface would have to move faster than the speed of light, which is actually impossible for electrons to do according to Einstein's theory of relativity. So it was at this point that scientists realized that the spin is not actually a spinning motion. Instead, the spin is an intrinsic quantum property of particles, which is essentially something that is a fundamental rule that simply that particles simply possess. So kind of like a mass or its electric charge. So similar to how a particle has mass, an electron also has spin. So it doesn't mean that it's spinning, but it just has this property called spin. Does that make sense, Goldie? Hopefully. Okay, chat, does that make sense? Spin is an intrinsic property of quantum mechanics. Spaghetti says electrons jiggle. Okay, so okay, thank you, Gerald, for the validation. I appreciate that. But okay, so we've established that electrons have spin, and so
Can I just say, I find it really funny that the definition of spin for electrons is not like spinning, it's something else. And, it kind of reminds me of like, when I used to be a politician and like, we would spin narratives, or the media will spin a story. And I'm like, oh, so it's like one of those sneaky spins.
Mm-hmm. Yes. Yes. We'll go with that. Okay, so guys, we've established that electrons have spin, and one consequence of an electron spinning is that every electron possesses something called a magnetic moment. Okay. So a magnetic moment is essentially a measure of how strongly something behaves like a tiny magnet. And this essentially means that every electron in the universe behaves like a microscopic bar magnet, kind of like this. So I'm trying to get it to focus. Every electron is basically one of these, acting like a microscopic bar magnet.
You know why it's not focusing? It's because I think the setting on your camera is set to automatically focus on a person on the face.
Oh, okay.
Your face is just so beautiful. Your face is like a magnet. It's like attracting the focus of the camera.
Oh my
It's
goodness, you're so funny. Okay, well, that's good to know for next time. But yeah, so you guys get the idea. So every electron is basically like a little bar magnet, and it's got a north side and a south side. So you can essentially think that every electron has its own tiny little north pole and south pole. And this realization essentially completely changes how we think about matter, because it means that every atom in the universe already contains these tiny magnets, literally everything, because everything has electrons. And so this itself creates a whole new mystery, which is, why isn't everything around us magnetic? And so the answer here comes down to what we call cancellation. So in most materials, these tiny atomic magnets, which all have these little north and south sides, are pointing in random directions. And so one might be pointing this way, one might be pointing that way, and like vice versa, all random. And when you add all of those tiny magnetic effects together, they cancel each other out. So even though every atom is magnetic, the material as a whole can be non-magnetic because of all of these pointing in different directions, which doesn't have any sort of net magnetism. Now, if the spins, which is that intrinsic quantum property that we talked about, if all of those happen to align in the same direction, so all of them are pointing up, for example, then you have something called net magnetism, and all of the magnetic fields in an atom line up, and you have a noticeable magnetic field. And then this is what happens in ferrous materials like iron or nickel and cobalt, for instance. So in these kinds of metals, you have billions upon billions of these tiny atomic magnets that start cooperating with one another and point in the same direction, in an effect called exchange interaction, which is another concept in quantum mechanics. So we're kind of starting to get to the building blocks of understanding why magnetism is created. But I'm going to have to explain this exchange interaction a little bit more in detail before we get to some of the more fun stuff. So, okay. So exchange interaction, again, like this is another quantum principle, but essentially electrons are these tiny, tiny quantum objects, and quantum particles don't occupy the same exact quantum state. So sorry, they don't.
Can I ask a quick question? Like, again, I'm not a sciencey person, so if I say something wrong, feel free to laugh at me. It's okay.
Never.
But whenever I think of quantum mechanics, I think of like Schrodinger's cat. Is that the right thing, or is that like a different thing. Like, you know, the whole, like, is the cat in the box or not? And you don't know if the cat's in the box or not until you open up the box. And so when you don't know, like, it's both in the box and not in the box.
Yeah. So I think it's like if you don't look, it's both alive and dead. But if you end up looking in the box, it's one or the other. So until you look, it like both states exist. And I think the reason why you're linking that is because Schrödinger was one of the founders of quantum mechanics, and he developed the Schrödinger equation. So there's definitely correlation there. So that's likely why you kind of think about that. But yeah, like it is a very interesting experiment, and Schrödinger developed an equation that kind of treats particles like electrons, similar to waves, rather than tiny balls of like particles following precise paths. So there's a whole other topic we can go over around like particles and waves, and this is kind of where some of that comes into play. But yeah, that's there's definitely correlation there, Goldie. Would you look in the box, Goldie?
No, because there's a 50% chance the cat is dead, and that would make me sad.
That's funny.
I would be like, oh, the poor Pishi. You know, usually I would say knowledge is power, but in this case, I would be like, no, I don't want to risk the cat not being alive.
That's really funny. But yeah, I mean, you know, you never know. So I guess it's good to know that you're more risk averse. You wouldn't want to risk it.
Well, I'm only risk averse when it comes to certain things, like, you know, animals, right? Because I love animals.
That's
but fair. You know, other things I'm actually quite, you know, aggressive.
Are you? You know what? I agree with that. Okay, so going back to quantum mechanics, but essentially, quantum particles don't like to occupy the same exact quantum state as one another. And so this is actually related to a principle called the Pauli exclusion principle, which essentially states that some identical subatomic particles, like electrons, can't occupy the same quantum state. And so because of this rule, electrons can actually lower the total energy of their system by aligning their spins in certain materials. And because physics as a whole loves lower energy states, in materials like iron, for example, and other ferrous materials, the lowest possible energy arrangement for these metals happens to be when many of these electron spins point in the same direction. So when they're misaligned, like in this top section here, this is actually taking up more energy for the material to remain in that configuration. And so in iron, for example, the lowest energy arrangement for that particular material happens when many of the electron spins are pointing in the same direction. So the question then becomes, if iron atoms, for example, are naturally aligning, then shouldn't every piece of iron that we have in existence already be a giant magnet? And so the answer is no, because this is where we get to something called magnetic domains. And so iron, okay, so magnetic domains are essentially, okay, let me organize my thoughts. So iron organizes itself into these regions called magnetic domains. And this is essentially where all of the atomic magnets within that material agree with one another. And so you have some sections in like one domain, for example, which are pointing up. You have another section where they're pointing down. you have another section where they're pointing sideways. But within each domain, everything is aligned. But since the domains are pointing in different directions, the magnetism once again cancels out. So this is why not every single piece of iron is intrinsically magnetic. Only when an external magnetic field forces all of these domains to point in the same direction does that piece of iron or whatever material you have become magnetic. And so that's actually how you create a magnet, Goldie. So you have to have this external force that comes in and forces all of these domains within a ferrous material like iron to point in the same direction. And then you have a permanent magnet like this.
So yeah, like I'm not a science genius like you. Is there like, do you have like a visual or something that can sort of like explain or show, like, assume that I'm like 5 years old, right? Like, how would you explain this? Is there like a video or something that you have that you could share to kind of like explain this from like a very beginner's perspective to someone like me who literally knows nothing about this stuff? And guys, like for everyone who's watching the live stream, I've always said like I have no problem saying like what I know and what I don't know. Like geopolitics, I know. Science and magnets, I don't know. And I'm here to learn. So I have no problem saying like I'm not getting this and I need like a, explain it like I'm 5 years old type of video or something.
Okay. So I have a video. It's about 1 minute long. I haven't watched this, so I don't know how good it is, but we'll explore together and we'll see how elementary it is. Okay. Okay.
You know what? I like this already. There's a magnet with a face on it. I feel better already. Like
let's test this out. And
that's Magni the magnet.
Okay. Okay, let's test this. I can't hear anything. Can you hear anything?
No, is it not speaking?
Oh, you're wondering why this paper pin turned into a magnet and why this paper pin is attracting other pins? Listen, when you rub some metals with some magnets, these materials also acquire temporary magnetism. It's related to domains. Every metal has electrons inside, and these places are called domains. But these electrons are lying in a haphazard manner. They keep canceling each other's attraction power. So these metals don't attract like magnets. But when you bring these metals near some magnets, all the electrons get aligned due to attraction of electrons in the magnet. This alignment of electrons creates magnetic power in these metals. You are a funny man. You're trying to make this paper a magnet by rubbing it with other magnets. Remember that only a few things are turned into temporary magnets by rubbing it with magnets. It doesn't happen with everything. Oh, are you putting a magnet's north pole towards my south pole? Oh, are you trying to attract...
What? Okay, but okay, so that was a very interesting video, but the visual with the magnetic domains, can you go back to that? Because that was interesting.
Pull toward putting rubbing magnet your power in these
the
metals.
Clip?
This alignment align, but when you bring these metals near some electrons are lying as electrons inside.
Yeah, pause. So when you're talking about them, like, so if I understand what you said, then each of those rectangles is like a magnetic domain. And then the arrows pointing up and down is what keeps it from not being magnetic.
Yeah, because they cancel each other out.
Right, they cancel each other out. But then when all of them are pointing in one direction, either north or south, that's when it becomes magnetic.
Yeah, so that's when you essentially need an external force to play a part in changing the direction of all of the different domains to become the same. And then that's when you have a permanent magnet. And this is actually a great time to talk about temporary versus permanent magnets, because you can have both kinds. So let me stop this.
Guys, by the way, that was my video that I wanted Rose to explain to me. So I didn't realize it would end that way. So you can't blame her.
That was a great video.
Because I was like, wait, what are magnetic domains? So I was like, Rose, like, what about this video? And then there you go. Totally my fault.
No, it's fine. It was kind of funny.
It's like a floating, talking magnet. Oh my gosh, that was so weird.
Yeah, it was definitely something. But okay. So let's go back to like the difference between permanent and temporary magnets, because you have both kinds. So essentially a temporary magnet only stays magnetized when an external magnetic field is present. So you essentially need you need this, which is a permanent magnet, this acting on, let's say, something like, so this is a piece of iron. It's an iron bolt, nut.
Which one?
It's a nut. It's a nut. And so this has become a temporary magnet because this permanent magnet is exerting its force on this temporary magnet. And so now you have this temporary magnet with this permanent magnet. This is always going to be magnetized. So even if there's no other external force acting upon it, it's always going to stay magnetized. But in a temporary magnet like this, the magnetic domain aligns when it's exposed to a magnetic field, such as this, for example. And then once this is gone, it like quickly becomes randomized again when that field is removed. So in the permanent magnetic version, that magnetic domain always remains locked in place, even after the external field disappears. And this essentially happens because the internal structure of the material itself makes it energetically favorable to stay aligned in that configuration, because it requires less energy to do that. So you have temporary magnets like this. You have permanent magnets like this, which always have that field. And then there's actually a third type of magnet.
Before you go to the third type of magnet, so I kind of missed it, or maybe you didn't explain it yet. So what makes a permanent magnet permanent?
So you need a very, very strong external force to permanently move all of the domains in one direction.
Okay, so all of those little like squares that we saw with the arrows going up and down, now that I've visualized it with Magni the magnet, the talking magnet. Okay.
Yeah, okay. And then so you have the third type, which is an electromagnet, which is a magnet that's created by electric currents. So when electricity is flowing through a wire, it generates a magnetic field. And when the current stops, the magnetism also disappears. So these two things work together. And so this is actually one of the fundamental discoveries of physics, which is that moving electric charges create this magnetic field. So if you wrap, for example, a wire into a coil and then run an electric current through that, the magnetic fields from each of those loops add together and create a strong magnetic field. And if you place an iron core inside of that coal, for example, the iron's magnetic domain aligns with that field, making the electromagnetic a lot stronger. And so, unlike a permanent magnet, an electromagnet can be turned on and then turned off. So you have that control based on the electric current and by changing the electric current as well. And so, Goldie, electromagnets are actually used every day, all the time, in things like motors, generators, MRI machines, like a variety of just everyday items. It's something that's very, very common and that we use all the time.
And you know what? Someone was actually asking about fridge magnets.
Yeah. So fridge magnets are a type of permanent magnet because they always have that permanent magnetic field. They're magnetized, and so fridge magnets are a type of permanent magnet.
So, like, just so I can understand, like the way that a magnet becomes permanent is from like an external force, and then usually that external force is like, for example, when you know people are making magnets in factories or something, that external force is like electricity or something. So they wrap a piece of metal in like electrical coil or something and like just generate electricity until it becomes permanent. Is that how it works?
So I think electromagnetism can be used. I think that's one way to create a permanent magnet, to permanently change the domain within a ferrous material to all point in the same direction. And so when that strong magnetic field from another source is applied, whether it's through an electromagnetic current or through other materials. So there actually are some existing elements and materials. Neodymium is one of them. So it's actually a rare earth metal. I think it's element number 60, if I'm not mistaken. So those can also sometimes be used to create other kinds of permanent magnets because they're quite strong. And so they can also contribute to the development of some of those permanent magnets as well.
Okay.
Okay. So we've talked about magnets. We kind of know, I hope, ish, how magnets are created. The next question is, what is a magnetic field? So the magnetic field is basically the next step of like understanding how magnetism works. So when we think about what happens when we have two magnets close to each other, how does one magnet know that another one exists and knows whether to like repel or like attract it? It doesn't like have eyes, right? As far as we know, like we don't know how it knows what's going on there. And so this is actually where physicists developed this idea called the field concept, which essentially states that magnets don't actually interact directly with each other, but instead they modify the space around them. And so this modification of space is what we call a field. And so a field is essentially a physical quantity that has a value at every point in space. And so like an easy example to kind of think about is something like temperature. So to paint a picture of what that could look like let's say today in Toronto, it was 77 degrees Fahrenheit. Tomorrow in Ottawa, it's going to be like 68 Fahrenheit. Vancouver might be like 65 Fahrenheit. And so if you painted all of this in one temperature map, you kind of have a representation of a temperature field. So the temperature exists whether or not you're standing there to measure it. And that same thing is true for magnetic fields, because at every point around a magnet, the space itself has been altered. And so when physicists are talking about a magnetic field, they're talking about a specific quantity that exists everywhere around a magnet. And so at every point in that field, you have two specific properties. The first one is the strength, which is how strong a magnet is. And the second one is the direction, which is which way would another magnetic object move based on that field. And so to kind of give a visual representation of what that looks like, I have like a 30-second video of a visualization of a magnetic field taken from iron filling. So I'm going to share my screen here. Okay, so this is really quick, but it's basically a magnet similar to this with a north and south side. And they're going to pour some iron fillings on it. And then you're going to be able to actually see a visualization of what that magnetic field looks like.
Can you maximize that?
Okay, let's watch that one more time.
Mm. So he just like sprinkles like iron little
Iron
pieces
fillings on it.
Yeah. So is that what the magnetic field around the Earth looks like then?
Yeah, very similar to this. It has a very similar pattern where the magnetic fields are going from the north to the south, the magnetic north to the magnetic south. I have to specify because there is a difference. But yes, and we're going to go into that a little bit as well. But essentially, the iron fillings demo works like this because each tiny piece of iron essentially becomes a temporary magnet in this situation. So we went over temporary versus permanent. So the bar is your permanent magnet. The iron fillings are temporary magnets when it's placed on that external magnetic field. And then the iron fillings themselves contain billions and billions of electrons whose magnetic domains can easily rotate. And then when you place the fillings near a magnet, the magnet's field forces the domains inside each of the filling to align. And then each filling then becomes its own tiny little magnet with its own north and south pole. And the fillings experience forces from the magnetic field and from the neighboring fillings, causing them to kind of line up in the shape that they do, demonstrating the curved patterns that trace out what the magnetic field lines actually look like. So really, really cool. Well, I think so.
I think it's super cool.
Okay, so next I want to briefly touch on electric fields because electricity and magnetism are both essentially manifestations of the electromagnetic force. And so electric charges, I mentioned before, create something called an electric field. And moving electric charges create magnetic fields. So electric fields and magnetic fields are both deeply, deeply connected. And I'm actually going to touch on the theory of general relativity here quickly, because according to Einstein's theory, magnetism itself is actually a relativistic effect of electricity. So for instance, if you're standing still and looking at an electric charge, you yourself might only be observing an electric field. But if you start to move relative to those charges, suddenly you can observe a magnetic field as well. So magnetism itself is built into the structure of space, time, motion, and electricity itself, which is quite fascinating. So now that we have a basic understanding of how magnets work and how the magnetic field works, let's talk about what happens when the thing that's creating the field of an entire planet. Let's talk about Earth, because Earth itself is a giant magnet, and it's surrounded by a gigantic magnetic field. And that invisible field is contributing to the development of the invisible force field that we talked about, and is contributing to one of the reasons why we're all here today. And so essentially, to recap everything we've talked about so far, electrons create magnetic moments. Moving electrons create magnetic fields, and organized motion can create very powerful magnetic fields. And so when some people hear that Earth is a giant magnet, for example, they imagine something like maybe like a gigantic bar like this sitting inside the middle of the Earth. But that's actually not possible, because permanent magnets lose their magnetism when it gets too hot. And this is actually something called the Curie temperature, which is the temperature above which a magnetic material loses its permanent magnetism. And Earth's core is actually way, way too hot for that, and way too hot for any sort of like actual metal like this to explain why Earth is a magnet. But we're going to get into exactly what that means and what that looks like. So I have another diagram for you guys. Share screen. Okay. Let me remove the chat for a second while I go over this. Okay. So, so guys, Earth's interior temperature is enormous. It's the core of Earth is over 9,000 degrees Fahrenheit, and so the Curie temperature for iron actually, so that's when iron loses its magnetism, is around 1400 Fahrenheit or 770 Celsius, meaning it's way, way too hot in the core of the Earth for any sort of permanent magnet to actually exist. Yes, Omid, sorry, I just saw this right now. I was hoping, oh, sorry, wrong comment. I was hoping someone would catch this, but yes, it is over 9,000. Okay, so let's take a quick tour inside Earth. So we got our crust, which is essentially the outer section of the Earth. We have the mantle, we have the outer core, and then we have the inner core. So the crust is the thin rocky shell that's on the outside, and this is where we all live. The mantle is the next stage, which is a thick layer of very, very hot rock. And then we have the outer core, which is liquid and is made mostly of iron and nickel. And this is the only liquid layer of the planet and is actually very key to Earth's magnetism. And then finally, you have the inner core. And the inner core, we're back to solid, and is made up of mostly iron and nickel. And the reason it's solid here is because of the immense pressure. So the extreme weight of the planet compresses the iron and nickel alloys here so tightly that the melting point rises dramatically and prevents the metal from becoming liquid. So because the outer core experiences less pressure, the iron there remains liquid. And as I said, this is the key to where that magnetism comes from. So earlier we learned that that moving electric charges create magnetic fields. And so molten iron, which is in the outer core, is essentially is electrically conductive. And so inside Earth, this liquid iron isn't sitting still. So it's constantly moving. And the reason for this is due to the heat from the inner core. So the heat from the core of the Earth is escaping from that interior, and it drives these convection currents, which essentially means that the hot fluids are rising and the cooler fluids are sinking. And so this is actually creating these enormous circular currents of liquid iron within the outer core of the Earth. And so that's the first step. And then on top of that, there's another ingredient, which is Earth's rotation. So Earth has one full rotation every 24 hours, or 24 Earth hours, because time is relative. And that rotation is twisting and organizing the flow of liquid metal. And this is actually an effect called the Coriolis effect, which is causing these giant flows of liquid metal to organize themselves into these large-scale spirals and columns. And as the electrically conducting iron is moving around, so this is the liquid iron, it's starting to generate electrical currents. And so these electric currents actually produce a magnetic field called a geodynamo. So you have heat from the inner core. Let me just adjust this diagram. Okay. So you have heat from the inner core, creates these convection currents. Earth's rotation is twisting that flow. And then the moving liquid iron is essentially acting as a conductor. Magnetic fields are created, and Earth is becoming this giant magnet. And this process is called geodynamo. And so this is actually very similar to how a generator works. So generators work because moving conductors through magnetic fields creates electricity. And so they have a conductor, which is usually made up of a copper wire in the shape of a coil. And then this is where electricity is being created. And so you have a magnetic field produced by a permanent magnet or a very powerful electromagnetic. And then you also have motion, which is relative motion between the magnet and the conductor. So that's essentially the building blocks of a generator. And Earth is, in fact, doing the exact same thing. And so the result of that is this magnetic field that is extending far beyond Earth's surface and is actually going tens of thousands of kilometers into space. And so this is actually a region called the magnetosphere, which is this essentially this giant protective shield around our planet. So this graph is showing the what the magnetic field could look like. Looks like on Earth. This part is interesting because I want to touch briefly on geographic and magnetic north and south poles. So the geographic poles are defined by Earth's axis around its rotation, while magnetic poles are defined by Earth's magnetic field. And they're not actually in the same locations and don't behave in the same way. So the geographic poles are kind of always consistent, whereas the magnetic poles can sometimes shift. This can sometimes be confusing because the magnetic North Pole is located geographically near the geographic North Pole, but it's actually magnetically a South Pole because a compass, if you think about a compass pointing north, it's being attracted to a south field. So it can get a little confusing, but yeah, I thought a graph would hopefully help a little bit in terms of how it could be described. But compasses essentially point towards the geographic North Pole, but that region must be a magnetic South Pole, even though we call it a magnetic North Pole. Clear as mud. Okay, and so I think that is, let's see. So let's talk briefly about what the magnetic field is actually protecting us from, and we're going to go more into this specifically, but so we essentially have all of the background info now of understanding how the Earth is actually a magnet. And so what would happen if Earth's magnetic field disappeared? And like, should we even care? But the answer comes down to space, and space not being a very friendly place. So specifically, space can be very violent. It could be a very violent environment. And one of the biggest threats to Earth is actually coming from our very own sun. And so the sun obviously is wonderful, and it gives us life and light and heat and weather, and is basically one of the reasons why we're all here, and it gives us all of the energy. And without the sun, like, obviously we would be dead. Like, we've had this conversation before. But the sun is actually continuously trying to kill us. And beyond just producing light, the sun itself is also continuously ejecting enormous amounts of these charged particles into space. And this stream of particles is called solar wind. So obviously the sun is incredibly hot, and the surface of the sun is over 10,000 degrees Fahrenheit. Hold on, I have another diagram for you guys. Okay. So the sun, obviously, it's very hot. It is around 10,000 degrees Fahrenheit, if not more. But the sun's outer atmosphere is actually hotter than that. Sorry, I'm trying to get this diagram to fit properly. Okay, that should be good for now. But okay, so the sun's outer atmosphere, which is called the corona, so it's even hotter. It can reach temperatures of around 3 million Fahrenheit, and at those temperatures, atoms are getting ripped apart, electrons are separating from nuclei, and you end up with something called plasma, which can sometimes be referred to as the fourth state of matter. So the first three states we're all used to is solid, liquid, and gas. And then this fourth state, you have this ionized gas or plasma, which mainly consists of things like protons and electrons and helium nuclei moving incredibly fast and sometimes hundreds of kilometers per second and are constantly streaming away from the sun in all directions every second, all the time. And so this is actually what solar wind is. And so while these solar winds are constantly bombarding Earth, we are actually being protected by our magnetic field, which is essentially acting as this giant shield protecting us. So this is called the magnetosphere. And so because Earth has the magnetosphere, this is what's helping to protect us. So let's imagine like a particle coming from the sun towards Earth. Eventually, it can reach Earth. And when it does, it encounters Earth's magnetic field and it experiences a force. And instead of hitting the atmosphere directly, many of them actually get deflected because the magnetic field literally changes their trajectory and bends its path and redirects it away from the Earth. And so this is actually why many solar particles end up getting diverted away from Earth rather than crashing into us. So I have a little 4-minute video that I want to show you guys talking specifically about solar winds. So this is a video from NASA Science called NASA Science Casts Effects of the Solar Wind. So let's see what they got to say, and that'll give me a couple minutes of speaking break.
Effects of the solar wind.
Oops. Playback speed 1.
Effects of the solar wind. Presented by Science at NASA. The wind speed of a devastating Category 5 hurricane can top over 150 miles per hour, or 241 kilometers per hour. Now imagine another kind of wind with an average speed of 0.87 million miles per hour, or 1.4 million kilometers per hour. Welcome to the wind that begins in our sun and doesn't stop until after it reaches the edge of the heliosphere, the solar wind. The corona is the sun's inner atmosphere, the brightness that can be seen surrounding an eclipsed sun, and home to the continually expanding solar wind. Right now, the Parker Solar Probe, a NASA mission launched in 2018, is orbiting the sun and will get as close as 3.83 million miles, or 6.16 million kilometers, of the sun's surface. Parker is gathering new data about the solar particles and magnetic fields that comprise the solar wind. More specifically, two of its main goals are to examine the energy that heats the corona and speeds up the solar wind, and determine the structure of the wind's magnetic fields. While many theories describe the solar wind's history, this is what we do know. The solar wind impacting Earth's magnetosphere is responsible for triggering those majestic auroras typically seen at locations close to our north and south poles. In some cases, it can also set off space weather storms that disrupt everything from our satellites in space to ship communications on our oceans to power grids on land. Nikki Fox is the Division Director for Heliophysics at NASA headquarters. She explains in more detail how the solar wind disrupts our magnetosphere. As the wind flows toward Earth, it carries with it the sun's magnetic field. It moves very fast, then smacks right into Earth's magnetic field. The blow causes a shock to our magnetic protection, which can result in turbulence. NASA also has another reason to study the solar wind and its properties. The solar wind is part of a larger space weather system that can affect astronauts and technology. As Fox notes, we not only have to ensure our astronauts are protected from the harmful effects of radiation, we have to protect our equipment too. So we've already found aluminum to be a good shield to protect our crafts from many energetic particles. But there are also faster particles that travel at 80% of the speed of light, which can cause havoc with parts of a spacecraft. They can smash into and damage solar panels, disrupt electronics, or affect electric currents that flow along power grids. So we're currently conducting tests with small pieces of technology to study how well they can survive in intense radiation areas. Knowing more about the effects of the solar wind is not only important to those of us who live on Earth, it will be critical to know how to mitigate its effects once our astronauts travel back to the moon and beyond for extended periods of time. Fox concludes, "My feeling is, if the sun sneezes, Earth catches a cold, because we always feel the impact of what happens on the sun thanks to the solar wind." Get blown away by the science behind the solar wind at science.nasa.gov.
Get blown away by the science of the solar wind, guys. Okay, so I thought that was a pretty cool video to kind of show what the solar winds could look like. Hold on, let me change this view here. But yeah, so I think what was interesting about that video and what I'm actually going to touch on next is the auroras, because auroras are it's actually something that comes up quite a bit when you talk about solar winds and solar storms and things like that. And we saw it briefly in the video as well. But essentially, not all of the particles that come from the sun end up getting reflected, and some of them actually manage to travel along Earth's magnetic field lines, and they converge at the poles, which ends up leading to one of the most beautiful natural phenomena that we know, which is the aurora, or the northern or southern lights. And the way this works is that the charged particles from the sun travel down Earth's magnetic field lines, and then they eventually slam into atoms in our atmosphere, primarily oxygen atoms and nitrogen atoms. And then when these atoms are hit, they absorb that energy. And then when the energy ends up getting released, they emit light. And then that's actually what we end up seeing when we look at the aurora. So we're literally watching particles from the sun interacting with Earth's atmosphere, and the different colors that we're seeing, such as the greens and the reds and the purples, come from different atoms emitting different wavelengths of light. Goldie, how about you tell us your experience with the aurora? Because I know you've seen this before.
I was actually going to ask you, but because I feel bad. Well, that's when we traveled to Yellowknife. Like, this was like 15 years ago or something, and we wanted to see the aurora borealis, and we thought that we had to like be outside at 2 a.m. or 3 a.m. And this is back before internet or chat GPT or anything like that, so there was no way that we could even check, like even like our phones didn't even have access to data, right? Yeah. So this is like way before information was publicly accessible. So it was only after you left and I stuck around for my conference that we went to this place to see the aurora borealis. And the aurora borealis came around I think 8:30 or 9 o'clock or 10 p.m. And oh my gosh, it was like the most insane thing that I've ever seen. Like, it was so beautiful. And I felt so much regret because I was like, Rose and I, we tried so hard. Like, every night we were like, we want to see the aurora borealis, but we would go, go outside at we would go to sleep and then wake up at 2 a.m. to go out. Meanwhile, we should have been going out at 9 p.m. and we would have seen it all. And oh my gosh, Rose, it was the most beautiful thing. It was literally these dancing flames on top of my head. And it went on for an hour, and it wasn't dim, it wasn't blurry. It was so crisp and clear. And the entire sky was like red, green, purple, blue. So the most beautiful thing. Like we need to do like another trip um to Yellowknife and go see the aurora borealis. Like I really really want to go back. And I have to go back with you so we can experience it together.
I know. I can't believe you ended up seeing it without me, but you know what? I'm glad I'm glad one of us did. You know, we just didn't know how to do it right. And like honestly, the internet and like ChatGPT has just changed how we travel so much in general and can like know these things in advance. But yeah, that was definitely an interesting trip. And I'm really glad that you got to saw it. But you know, we're going to watch a quick little time-lapse video now, just of the aurora, just to admire some of the beauty there and what that looks like. Because, you know, I'm still living vicariously through you, Goldie. And
What life goals? We will go. We will go. I promise you, we will go. And you know what? Who knows? Maybe if the Gamma Ray Report becomes very, big and popular, you could actually go back and you could maybe do like a live stream
oh wow,
of the aurora borealis.
that would be cool. Guys,
Right?
let us know in the comments if you want to see that.
Like, would you be interested in Rose going up north to northern Canada and doing like a live stream of the aurora borealis?
Yeah, so beautiful. Just like look at that. So
The-
amazing, right?
Rose, that's exactly what I saw. Oh, you forgot the music.
Well, because I didn't want to do it on top of you speaking, but
That's okay. Put the music on. I'll stop speaking. Go back to the beginning.
no, you don't have to stop. It looks like fire in the sky almost.
This is exactly what I saw, like the green and the purple. Oh my gosh.
This is a time lapse, guys, so like it is sped up a little bit.
Yeah, that's exactly what I saw. Like this right here.
You saw, like, did you only see green or did you see other colors as well?
I saw all colors, purple,
Oh,
pink,
nice.
like the whole thing. And it felt so close, like you could just touch it.
She likes to open it, that's why.
Oh no! Listen, I can't tell her. Oh wait, why don't you stop the music? There we go. So I can't tell her that it was so cool and you didn't miss much because it was absolutely super cool, but who knows? Like, this will encourage her to expand her channel. But you know what's really cool, Rose, is I've seen so many amazing pictures of the aurora borealis from the perspective of space.
Mm-hmm.
And, you know, I don't know if you want to share some of those images or not, but
That's a great idea, Goldie. Yeah, so these are some, like the ones up here. This one's from NASA.
like that's so cool. Look at that. Like it looks like this layer. Do you want to click on it to make it bigger?
Yeah, hold on, I'm just doing it. It's in a different tab. Let me see.
Yeah. Like it just looks like this green like layer on top of the earth that's floating.
I know.
And
Absolutely beautiful.
what you're saying is like this is all because of magnets and like the magnetic field around the earth, basically.
So it's the solar particles that are being deflected away from the Earth's magnetic field and are converging at our poles, and they're interacting with our atmosphere and the atoms in our atmosphere. So like the oxygen and the nitrogen primarily that are being affected at the poles. And so that's why maybe let me go back to.
So is that why like you only see the aurora borealis at like the north and south poles, because that's where like the magnetism is like centered?
So let me share this tab. So most of the particles from the sun are deflected away by the electromagnetic field of the earth, but not all of the particles get deflected. So some of them end up interacting with the earth, and it typically happens at the north and the south poles where they converge. And then when that convergence happens is where you have the auroras. And so that's why they're at the north and the south pole. So it's actually happening because these are the particles that aren't being deflected away by Earth's magnetic fields. And so they end up interacting and slam into the atoms in our atmosphere. So these are the particles from the sun slamming into atoms in Earth's atmosphere, primarily oxygen and nitrogen. And then when these atoms are hit, they absorb this energy. And then upon release of that energy is when they emit this light. And so that's what we're actually seeing in the auroras. So you're literally watching these particles from the sun interacting with Earth's atmosphere. And so the different colors are coming from the different wavelengths of light that are emitting different colors based on the type of atom that they're interacting with.
Wow.
Yeah. So that's pretty cool, right?
That was super cool. That was absolutely super cool. And no, like these graphs and images that you're showing are just, it's phenomenal. Like it's really okay, so I don't know if you've answered this. Maybe you have. And if you have, I apologize, but I'd love if you could repeat this question that I have. So why is the Earth magnetized? Why do we have a North Pole and a South Pole? Like, does that mean the Earth is a giant magnet or something? And that's why, like, this is happening? I know you're laughing at me because it's like a silly question. You're like,
No, I'm not laughing. It's because it's literally what I've been explaining for the last hour.
No, I know. I know it's what you've been explaining for the last hour, but like, because you've gone over so many details,
Yeah.
and it's really like really helpful. But so based on like all of the knowledge that we've now learned about magnets, so like, you know, it may be like one or two, you know, let's say like a paragraph, 4 or 5 sentences. So why is the Earth magnetized?
Okay.
Now that you've gone through all the basics, I guess this could be like a good summary of like all the info that you've shared with us.
Okay.
I know she covered this 20 minutes ago, guys. I'm not a sciencey person.
No, it's fine. It's fine. And you know what? This is actually a great question because it's going to force me to like condense the last hour and a half into a paragraph. So let me take another sip of water. So I think I'm going to put up this graph because I think this was really what helped me explain it previously. But okay, so essentially, Earth is magnetized because its core contains a huge ocean, essentially, of electrically conducting liquid iron that is constantly moving. Okay, so Earth has this outer core layer that is liquid iron and nickel, and it's the only liquid component of the Earth. And so this is constantly moving. And these moving electrical currents are generating Earth's magnetic field. So Earth
so the middle of it is like a giant magnet, basically.
Kind of, but it's not like a magnet in like this form. So it's not like this bar of magnet.
Yeah, no, it's not like that because that's solid. That's not moving.
Right. But the reason it's not is because it's actually way too hot for any sort of permanent magnet to exist in the center of the Earth. So there's something called the Curie temperature, which is essentially when a metal gets demagnetized and the center of the Earth is way too hot for any sort of permanent magnet to actually exist there. So what's actually happening, because there's no sort of permanent magnet, instead you have these moving liquid metals that create electricity. Okay, so you have heat that's escaping from the core. So the core of the Earth is solid. Okay, so this part is solid. This part is liquid. Okay. So the solid part of the Earth is you have heat that's escaping from the core, which is driving convection. And convection is essentially when hot material rises and cool material shrinks. This is what's happening in this liquid compartment of the Earth. And so that motion is causing the liquid metal to move and is creating this electricity. Now, that's only one half of the equation. The other half of the equation is Earth rotating. Okay, so I'm going to come down here. So this is this process that I'm explaining right now. So Earth's rotation is causing something called the Coriolis effect, which organizes the moving liquid into these organized flows and these organized swirling patterns. And so Earth essentially rotates once every 24 hours. So that's what we call a day. And so this organized rotation is creating these organized flows of this liquid metal into these large patterns, which essentially create this conducting fluid with electrical currents. And so those electrical currents generate the magnetic field. And this is a self-sustaining process called a geodynamo. Does that make sense, Goldie?
It does because you've already gone over every single one of these steps in detail. I feel like this summary now, especially this part of your graph where you kind of have like the different steps, it makes sense because right now, like you were just explaining like step number 3 and 4. So yeah, no, it absolutely makes sense to me. And awesome. I say this as someone with like no science background, right? But yeah, like I always feel like having like a concise summary at the end of like a long explanation, like definitely like, no, this makes sense.
Okay, that's great to hear. And so, yeah, so when you think of Earth being a magnet, it's not because of that permanent magnet that we have. It's because of all of the moving liquid metal creating the electricity. And so Goldie, that's what creates the electromagnetic field that we see here.
Mm-hmm.
And so the question now is, what would happen if we don't have a magnetic field? So let's say Earth's magnetic field disappeared. What would happen? So we wouldn't.
I know, compasses would stop working.
Yeah.
We wouldn't have a north and south.
I know.
Like fridge magnets wouldn't work. I don't know.
That's so funny. Yeah, you're not wrong. So yeah, if Earth's magnetic field disappeared, compasses wouldn't work. But I mean, it wouldn't be any sort of like apocalyptic event, at least like not right away, essentially. We wouldn't instantly die, but we would become a lot more vulnerable. So there are definitely some short-term effects, which include increased exposure to radiation from the sun because of all of those like things from the sun, like the solar storms and all of the solar winds coming at Earth and all of the radiation from space. So some of the short-term effects will include increased radiation exposure, which can lead to some serious health effects. There can be satellite damage, disruptions with GPS and compasses, Goldie, different sort of communication failures. It would definitely affect animals because a lot of animals use magnetism for things like migration and moving around.
Like birds and stuff?
Yeah, exactly.
Birds and butterflies. I know butterflies migrate.
Yeah, definitely. Insects use magnetism, and it's very common in animals. There would be issues with communication, electrical grids. So for things like satellite and GPS specifically, the Earth's magnetic field helps reduce these two exposure from damaging radiation, similar to humans being protected. These electronics are also being protected by radiation. And so that radiation, if we don't have a magnetic field, could certainly interfere with the different sort of electronics and communication signals that we have. So during any sort of major solar storm, there are disturbances on Earth with the magnetic field that can disrupt GPS accuracy and different radio communications and different satellite operations, even because they can be susceptible to this kind of radiation. And then for our electrical grid specifically, during a major solar storm, Earth's magnetic field can fluctuate over huge regions in our planet because power transmission lines sometimes can stretch for hundreds and hundreds of miles or kilometers and effectively act like these giant massive antennas that like span across the planet. And so changing magnetic fields can induce electrical currents within those long wires. And so this is like power essentially going through those lines that isn't being generated by the power companies. And so those extra currents can flow into transformers and cause them to overheat and malfunction and fail. And this has happened before, Goldie. So it's happened, like we've seen solar storms disrupt technology before. There was like a very famous Carrington event in the 1800s, which was the strongest solar storm ever recorded. And like even more recent in the 80s, there was a massive blackout that happened in Quebec, where this powerful geomagnetic storm struck Earth, and it overloaded a lot of electrical currents in the Quebec power grid, and it was also devastating there. So there are certainly some of these effects that can take place, and so those are some of the short-term effects. And then you also have some longer-term effects. So the longer-term effects can potentially be more serious because magnetic fields don't just protect us from individual solar storms, but they also help protect our atmosphere and our geology over time. And so to understand why this specifically matters, we need to look at another planet. Can you guess? Yes. You're so smart, Goldie. Okay,
No, I just figured it's Mars because we rely on Mars for a lot of like data and stuff, right? So I just figured it's Mars.
yes, you are.
Because apparently the theory is that Mars maybe used to have an atmosphere and water and stuff, and then it rusted or something because it lost its atmosphere.
Yeah. Yeah, so there definitely are some similarities. So obviously, like, Mars wasn't always the planet we see today. So hold on.
I love how you say obviously as if like we're supposed to know what Mars was like
Oh, I'm sorry.
5 billion years ago. Like a smarty
Sorry.
pants like you. And I'm choosing. I'm choosing like, but
No, I didn't mean it that way.
no, it's okay. No, no, you're very smart. I'm just showing how not intelligent I am. But I think it's really cool that like the reason Mars is red is because it's rusting.
Yeah.
And it's rusting because it doesn't have an atmosphere, and it doesn't have an atmosphere because
it does have an atmosphere. It's just very, very like minimal. Like it's like tiny, but yeah, like it used to have
with like magnets or something, right?
Yeah. So okay, so Mars definitely wasn't always this like red planet that we see today. So there is evidence that suggests that billions and billions of years ago, Mars may have actually looked quite similar to what Earth is looking like today. And so scientists believe that ancient Mars likely had things like rivers and lakes and a much, much thicker atmosphere and possibly even some oceans similar to Earth. And so it could have been a lot more Earth-like. But and also on top of that, scientists think that it could have also had a magnetic field, which it no longer has today. So Mars does not have a magnetic field. And so early Mars appears to once have had this dynamo. So similar to how Earth is this geodynamo today with the moving liquid metal in the core. Mars appears to have also been like that, with some sort of liquid metal core that was moving and creating these electric currents, which generated that magnetic field. And the reason we know this is because when spacecraft study ancient rocks on Mars, they actually find evidence that those rocks were magnetized billions and billions of years ago. So there's evidence of that. And rocks can only become magnetized if they're exposed to a magnetic field. So at some point in Mars's distant past, it appears to have had this global magnetic field, which it doesn't have today.
So that could possibly happen to the Earth. Because if it happened to Mars, it could happen to Earth. Oh my, that's terrifying. Oh my gosh. Okay, I was already afraid of, the Earth dying because the sun is dying. Now I have to add like another existential fear to like my fear of sciencey things, which is like, the Earth stopping being magnetic and then turns into Mars. Thanks, Rose. Thanks.
You're welcome.
Guys, yeah. Who needs geopolitics when we can just learn about how science is killing us, right?
That's so funny. But yeah, so science can definitely be scary. But at some point in this distant past, Mars had this electromagnetic field, and then something happened. We still don't really know why this happened, but the dynamo kind of shut down. One idea and one theory could be that because Mars is a little bit smaller than Earth, smaller planets can lose heat faster than the Earth. And so once the interior is cooled enough, the convection in the liquid core kind of it gets weakened. And then once the liquid metal stops moving efficiently, the dynamo could essentially shut down and then not work properly. And then so once that shuts down, the magnetic field also disappears. So there's no electric current being created, and so there's no magnetic field there. But scientists don't necessarily think that the loss of the magnetic field is the only factor that's contributed to how Mars looks like as a planet today. Again, like this happened over hundreds of millions of years, and there could have been multiple factors involved. But the loss of its global magnetic field is definitely one of the major events that scientists think why Mars went from that wetter world that kind of looks like Earth to the cold desert that we see today. And so, Goldie, in principle, the same thing could happen to Earth, but like but like, listen, like it's not something that scientists expect to happen anytime soon. Like Earth's core certainly still contains enormous amounts of heat. The geodynamo has been operating for billions of years, and most models suggest that it will still continue operating for billions of more years. So there's definitely other more pressing existential crises, I would say, we should prioritize over this. We're like not about to look like Mars anytime soon. Definitely not next week. Maybe next year, but not next week. That was a joke.
Oh gosh. Well, you know, I actually have a request for what I want you to talk about for next week.
Oh, what is it?
I don't know, guys. I don't know. Since we're on this whole theme of like every week you're like talking about one other way that like science could possibly like kill us and like end civilization and humanity. I don't know. Maybe would you or the chat be interested if you did a live stream on cordyceps?
Cordyceps. Ooh, like the zombie fungus that like takes over ants.
Yeah,
the whole show after it.
and that's the whole basis for The Last of Us, right?
Yeah. I would, I mean, I guess like it's you kind of like this morbid theme, I guess. So, let's just go with that and talk about the possibility of becoming zombie, real life zombies. But like,
or maybe the science behind cordyceps, right?
Yeah.
And how that works in The Last of Us. And like, I mean, I don't know. I'm just thinking like, listen, when you said that you're going to do a live stream on magnets, I was not expecting you to talk about like how the Earth could potentially like, die if we lose the magnetic field. And when I look at like all the topics you have here, like every single week, right? You're like, oh, nuclear, and then the sun is dying, and then like we would not survive without dogs, and then how tornadoes are killing us. And listen, magnetic field, I was like, okay, this should be fun. And then you're like, guys, if we lose the magnetic field, human civilization is gone, we turn into Mars. So
listen, so
you're the one who's like, kind of like, subconsciously bringing in like this.
Listen,
can kill us.
I was actually, so I came up, like I knew I was going to talk about magnets, but I had to find like something like exciting. Like magnets are exciting, but like the average Joe might not want to learn about like a magnet. So I was thinking on Friday, I was like, how could I make the topic of magnets exciting? So I'm like, oh, how about I relate it to like Earth's magnetism and like what would happen if, it disappears.
You did a fantastic job. Like, this is super cool. It's like, I always thought magnets were cool, but now it's like, guys, like we need magnets to exist and remain alive. So now, Javid magnets, Javid the magnetic field, like Javid magnetism, guys. We are a pro magnet channel. No like magnet deniers allowed. Anyone comes here and is like denying the magnetic field, like man.
That's
No,
so funny.
but you definitely made it interesting. Yeah, what are prions? Are prions?
Yeah, so prions actually, I don't want to get into it too much right now, but I just saw it in passing. But it's actually, so it's a disease that you can get from the brain, like ingesting brain, or like getting into contact with someone who has the disease somehow. But so it's essentially a kind of deformed protein.
I've heard about that. Yeah, and it's like something that you can't cure, and it's like it kills your brain or something.
Yeah, so
we just about that too.
It's terrifying. But like what's really scary about like prion diseases is that like one of the ways
meningitis is a prion disease, I think.
Oh, is it? I didn't know that.
I don't know. Is it?
I don't think so, because I think you could recover from meningitis. Like there's a like you have hope, but I think for prion disease, like you don't have hope. Like when you get it, like you're kind of done. And like the scary thing about prion disease is like sometimes it might not manifest until like
meningitis is not. Sorry, you're right.
Yeah. Anyways, but just another scary topic. But yeah, okay. So I'll write down cordyceps for the next one. That'll be a fun one just because I do really like The Last of Us. I'm actually not caught up on the last season.
Me neither.
And I don't want to give spoilers, but I watched like a couple episodes into the last season and then I wasn't really impressed and then I kind of stopped watching. But I really liked the first couple of seasons, so we'll just go with that.
Yeah, okay, but I think that would be kind of cool to talk about like the science behind cordyceps. And yeah, the prion is another one, like for sure.
I don't know, that topic like really grosses me out, like the prions. I'll kind of think about that.
Okay.
We'll see.
But I think people would be interested in knowing the science behind it, right? But who knows? But anyways, yeah, let's get back to magnets and how we literally rely on magnets to keep us alive. Thanks, Rose. No, yeah. But this is very cool. Like honestly, by explaining this now, like you just made like magnets and magnetism like 1,000 times more interesting and exciting because
well,
like we think of magnets as like like a cool little fridge magnet or a compass or whatever, but now it's like, wow, like guys, we are a pro magnet movement. This is the pro magnet movement here.
Javid magnets.
Javid magnets. There you go.
One thing I definitely want to touch on is pole reversal, because this is something that comes up a lot when people talk about Earth's magnetism. And so something interesting is happening, and so Earth's magnetic field is actually not static. So it's actually constantly changing. And so the magnetic poles are moving, and over Earth's history, the entire magnetic field has actually flipped several times. And so this is a process called pole reversal. And so the geographic North Pole is like the location of where the Earth's axis is spinning. And so the geographic North Pole doesn't move very much and is determined by the rotation of the Earth. But the magnetic North Pole, this is the point where Earth's magnetic field is actually pointing vertically downward. And this one moves a lot. So Earth's magnetic North Pole is currently moving. It's always moving. And scientists have been tracking its position for a very long time. And so historically, it's actually moved relatively slowly. But over the past little while, Goldie, it's actually started to accelerate. And this is happening like the reason this is happening is because Earth's magnetic field comes from like this molten lava that's flowing through Earth's outer core. And so that flow is actually quite turbulent and it's changing all the time. And so with that, the magnetic field that's generated by that flow is also moving, which means that the flow is also moving. So the magnetic
well, you're talking about the second layer of the Earth's core. Because it's moving around, that means that the magnetic field is also moving around. But of course, when it's moving around, it's not moving around as quickly. So, so how many millions of years or something does it take for like the magnetic poles to like switch?
So, okay, so that's an interesting question because there's not really any sort of like predetermined timeline around something like this. And I have another video that we're going to watch, which is going to explain this a little bit more. And it's going to go into that timeline a little bit more to explain when that's happened recently. But it's essentially like if and when this sorry, not if, like when this happens, it's not going to be any sort of like extinction event or any sort of like major disaster. It does definitely have serious implications. And the biggest thing is disruptions to technology and things like navigation and like increased exposure to space weather while Earth's magnetic field is kind of weakened during this time. But during this pole reversal, the magnetic field doesn't like turn off by any means. But it does weaken and it kind of reorganizes itself over time. But a weaker field would mean less protection from those charged particles from space and the sun. And it could have an increased risk to disruptions to satellites and GPS and radio. It could affect animals that use Earth's magnetic field for navigation, such as the birds and turtles and butterflies. And then they also need to kind of adapt to the changing magnetic patterns. But like there is geological evidence that shows that Earth has experienced hundreds of these pole reversals, but I don't think there's evidence that it's caused any sort of mass extinction events. So I want to put on the final video for.
Wait, before you go to that, you mentioned turtles and it reminded me of this video.
The I Like Turtles kid? Oh no. Zombie kid likes turtles. Of course.
It's like whenever I think of turtles, I think of this.
Back here live at the Waterfront Village with my friend, the zombie, Jonathan. You're looking good. Jonathan just got an awesome face paint job. What do you think?
I like turtles.
All right. You're a great zombie. And good times here at the Waterfront Village, open for the next 11 days.
Classic. Oh man, oldie but goodie. How old is that video? And how many views is it?
Okay, so I don't know. Like I just found the first random one. Oh, this one has. So this video was posted 19 years ago. It has 76 million views.
Oh my god.
Older
No, I'm not surprised.
You know what though? My favorite video ever is the one where the news reporter, I think it's like from Canada too, it's like Global News or something. He's reporting about like tobogganing and snow, and then like someone comes and he does like a somebody flips in the air. Have you seen that?
No.
Can I show it? Totally random, but it's too good.
Show it after this video.
Okay, all right. We'll go back to magnets.
You pull it up, and then meanwhile we'll show my.
We'll go back to the show. That was a little commercial break.
Okay. Too funny. Okay. Okay. So this, guys, is a video by an account called Astrum. And it's called What the Upcoming Geomagnetic Reversal Will Do to Earth. And it's our last video for this evening. So
When you think about the North Pole, you don't expect it to go anywhere. And you certainly don't expect it to change places with the South Pole. That would just be wrong. Our magnetic compasses would all point the wrong way. We'd need to update our maps.
That's what you said, Goldie.
Birds would probably be horribly confused. And yet, although they sound like something out of science fiction, geomagnetic reversals like this are real. They've happened before, and the process behind it might be a lot more dangerous than you'd think. To be clear, it's not the reversals themselves that are potentially dangerous, it's the buildup. During those times, the Earth's magnetic field, the shield around our planet that keeps us safe from deadly solar radiation, will drop to as low as 10% of its current strength, leading one group of scientists in 2021 to predict climate shifts and mass extinctions, and others to describe satellites being destroyed, electrical grids going offline, and deadly radiation raining down on us for hundreds or even thousands of years. This is troubling when you consider that we are a couple of 100,000 years overdue for our next geomagnetic reversal, and based on fluctuations.
Sorry, I just want to comment on that. I don't necessarily think we're overdue per se, because as far as we know right now, there's no clear indication of when these should be happening. So, like, I guess you can sort of say, like, it's been a long time since we've had this event take place. So maybe we should expect one, but I don't necessarily think that's a very scientific way to go about it.
Fluctuations in the Earth's magnetic field that scientists are detecting right now, the build-up to a geomagnetic reversal may even have begun already. Which begs the question, should we be worried? I'm Alex McColgan, and you're watching Astrum. Join with me today as we explore the science behind geomagnetic reversals and find out whether the next one will be an apocalyptic scenario or whether it'll lead to nothing more than a few lost birds. What truly happens when things go south? Let's start by trying to understand where the Earth's magnetic field comes from in the first place. It's not a given that our planet would have a magnetic field. The two planets flanking us, Mars and Venus, do not have one, and yet the Earth does, which is a good thing, as without one, there is a very real chance life would not have been able to arise here in the first place. Thanks to the protective cocoon of this field, deadly solar radiation is deflected away from the planet's surface, allowing things to flourish without all that radiation breaking down our DNA, causing mutations and cancers. Scientists are still trying to figure out all the particulars of why certain planets have fields and certain others don't, but the current leading theory is that the Earth's core acts as a giant dynamo. It's a principle of physics that you can use electrical fields to create magnetic ones, and vice versa. This is the principle that power plants work under. Moving a magnet through a coil of wires causes electrical current to start to flow, as that changing magnetic field exerts a force on the electrons present there. But similarly, the motion of electrons creates a magnetic field to form in perpendicular circles around the direction of motion, in accordance with Faraday's law of induction. But the way this applies to the Earth's core is a delicate, complicated process. To start with, our core needs to be at least partially liquid, which fortunately is true. Above the solid inner core that lies at the heart of our planet is a liquid outer core, where the pressure isn't quite high enough to keep things in a solid state. It's very hot in the outer core though, 6,000 degrees Celsius at its warmest point, so hot that it rivals the surface temperature of the sun, which, when combined with the lower pressure compared to the inner core, is more than enough to keep the iron and nickel that makes it up flowing down there.
So Goldie, like, if you think of it, it's actually these giant liquid metal oceans inside of the Earth that is protecting every living thing on Earth right now.
Sorry, could you repeat that? I was typing something in the chat.
Yeah, so I just like, it's cool to think about that it's like because of these giant oceans of liquid metal thousands of kilometers beneath our feet in like the core of the earth that is protecting every living thing on earth right now.
Not just protecting every living thing, but also like has contributed to the evolution or even like the existence of certain living beings, right? Like let's say birds or butterflies or like all these animals that rely on magnetic fields for their migration habits or patterns, right?
Yeah, exactly.
Wow.
Javid liquid metal.
Magnetic fields, yeah.
It drops as you move away from the center of the Earth. This gets circulation going. Hot, conductive material from the warmer, deeper regions of the outer core rises, then cools, then falls again, creating loops and currents of flowing material. Our electrical field starts to be generated. But if there are many of these flowing loops, which in theory there would be, why does Earth only have one North Pole and one South Pole? Surely the created magnetic fields would be all over the place. Well, there is thought to be an extra force at play that takes all these fields and unifies them, pointing them in the same direction. This force is thought to be the Coriolis effect. Dynamo theory states that the Coriolis effect causes these flows of iron to not rise and fall as straight lines, but as spirals. The spinning of the Earth causes them to gently be spun in turn, creating giant springs. As each segment of each spring is creating a magnetic field in a circle around it, the net result is that the inside of these springs creates a solid, unified field that all moves in the same direction upwards, while the outside brings that magnetic field looping back down again and back in to the bottom of the coil. In short, it creates the well-known magnetic dipole north and south that we see today. However, if there's anything that you should take away from this, it's that this process is precarious, as it is based on a lot of liquid iron essentially just sloshing around, which is not very consistent. Our magnetic field thus has little fluctuations and wobbles all the time. We see this in different ways, but a big one is that our North Pole is constantly moving. Since scientists began keeping track of it in 1831, the North Pole has grown.
So if the North Pole is constantly moving, does that mean Santa Claus is also constantly moving? Like, because Santa Claus lives in the North Pole, so how does that work with Santa?
So Santa Claus, Goldie, lives in the geographic North Pole, which doesn't really move because that's based on the Earth's spinning axis. The magnetic North Pole is what's constantly moving.
Okay.
As far as I know, correct me if I'm wrong, chat, Santa lives in geographic North Pole and not magnetic North Pole.
And so the geographic North Pole will always remain the geographic North Pole. So even if like the magnetic one moves, it doesn't affect the temperature or anything like that of the North Pole. The North Pole will always remain the North Pole, and Santa's always going to be up north?
I guess there could be some implications to temperature because of the changes to electromagnetism, but the location, like geographically, it won't change because that depends on the spinning axis of the Earth.
Okay.
But excellent question, Goldie.
Gradually shifted about 1,100 kilometers, leaving its original location in Canada and moving up towards Siberia. Its rate of motion is also increasing, going from 16 kilometers a year to roughly 55 kilometers a year, a big jump. This might still be akin to just the momentary wobbles of a spinning top though. Yes, it deviates somewhat, but it always remains roughly upright. That's a far cry from a complete reversal. However, scientists are certain that such reversals have happened before. They even have a specific number, 183 times in the last 83 million years. How do they know? The answer lies locked in our Earth's surface iron. When magma erupts from the Earth's mantle, it can contain small amounts of iron. As these can move freely in the molten magma, they tend to orient themselves in the direction of the Earth's magnetic field. However, scientists noticed that there were layers of geological history where the iron was pointing one way and layers where it was pointing in the reverse direction. Their explanation? The entire pole of the planet had flipped. On average, these flips seem to happen every 450,000 years, although the last few have only got 300,000 year gaps between them. Comparatively, it's been 750,000 years since the last reversal. You might think that we're overdue for one, and some have made that claim. However, scientists have found that there's little rhyme or reason to the timing of these flips. One of the longest gaps between flips took place in the Cretaceous.
Sorry, so that's what I was saying before. So like there's not really like rhyme or reason right now to dictate like when these reversals are
That's great to hear. So basically, we could wake up tomorrow and the magnetic poles could have just randomly flipped on us.
Right.
North and south. Yeah, it's like you wake up and it's like, surprise! North is south, south is north. Oh, great. Okay, so basically you just made my fear of magnetism like...
Oh my God.
Well, I mean, based on what you just said, like tomorrow, like the whole thing could flip if there's no rhyme or reason to this. Thanks, Rose. Thanks.
Well, as far as we know, like there could be, we just don't know it yet. But
okay, but if it happens tomorrow, I'm gonna, you're just gonna be like, surprise. Magnets, right?
Oh
Claim. However, scientists have found that there's little rhyme or reason to the timing of these flips. One of the longest gaps between flips took place in the Cretaceous period, and it lasted 40 million years. The record holder, the Kierman reverse superchron, was 312 to 262 million years ago, 50 million years with no reversal. Scientists are still trying to understand what causes these flips. However, the current theory is that something, perhaps some interplay between the mantle and the outer core, causes a fluctuation in the core spinning. This disrupts the spiraling shapes of the core's flow, breaking them down. The magnetic field of the Earth stops being unified and generally becomes a sprawling mess, fighting against itself. Several poles might temporarily arise during this period of shifting magnetic confusion. While in time things settle down and the spirals reassert themselves, it seems random as to which way they will do this, meaning about half the time our magnetic North Pole reappears over the geographical South. This reasserting can take 1,000 to 10,000 years. Alright, but would that really be the end of the world? Why does this matter? Well, during that period before the poles reassert themselves, our Earth's magnetic field drops to as low as 10% of its current strength. In theory, this could leave us much more vulnerable to all the solar radiation space throws at us. We could see auroras reaching much further south during that time. Skin cancer rates would increase. Our satellites would find themselves with not enough shielding. Radiation would fry their circuits, causing them to malfunction, shut down, and potentially even slowly fall from orbit. Our electrical grid would be much more vulnerable to solar storms, which could lead to large segments of the Earth's population without power. With no electricity or satellite communication, it would be a devastating blow to our global civilization. It could be worse than that. A research team from the University of New South Wales in Sydney even linked one of the most recent weakenings of the magnetic field, the Lachamps event, a temporary 800-year wobble rather than a full flip, to megafaunal mass extinctions in Australia, including the deaths of Diprotodon, giant Australian wombats, and Procoptodon goliath, giant kangaroos. Temporary wobbles like this are known as geomagnetic excursions rather than full reversals, and they happen over much shorter timeframes. Their transition periods can last as little as 200 years rather than 10,000, which can be much more difficult for species to adapt to. In their 2021 study, they argued that there was a spike in atmospheric radiocarbon levels caused by the collapse of the Earth's magnetic field, indicating climate shifts that could have led to these extinctions. The timing lines up uncomfortably.
Sorry, so just a quick point about that is, so the excursion is basically like a temporary magnetic disruption that doesn't fully go through a complete reversal. And so that's what he's explaining now. And there are some scientists who think that like this event is what could have contributed to some of the climate changes in history and some of the regional extinctions that we've seen in the past.
But how real are these risks? Honestly, it's a mixed bag. A point in our favor is that other than this recent study, there is no indication that magnetic field reversals have ever coincided with mass extinction events. It seems like many reversals have come and gone without affecting animal or plant life at all. And even in this study, such mass extinctions seem to have been limited in scope. There is no claim from the researchers that this was a global phenomenon. Other parts of the world remained unaffected, even during the Lachamps event. It seems that a perfect storm might have been in play, where specific conditions over Australia left it more vulnerable to solar radiation. In terms of our global society, it's worth noting that these magnetic changes would take...
Is this New York? Is anyone from New York?
Yeah, because I see like West 46 or whatever, so probably New York, plus the yellow caps. So quick question. Someone just mentioned in the comments, so, is this like, like the Ice Age? Did the magnetic field have something to do with the Ice Age? I don't know if we have an answer for that or not, but maybe that could be something to look at in the future.
Yeah, that's interesting. So the Ice Age,
I think that has more to do with the atmosphere, though, not necessarily magnetism. It seems like magnetism impacts like the atmosphere less.
Think about this for a second. So during an ice age, temperatures are generally cool enough for permanent ice sheets to kind of exist at the poles. And so within an ice age, you have some of these colder periods called these glacial periods. And now that I'm kind of thinking it through out loud, I don't think it's related to the shift in magnetism. The last glacial period peaked about like 20,000 years ago, which I don't think correlates to the last pole reversal.
Okay. No, I was only asking because just someone in the chat was asking if like, this shift impacted the Ice Age, and so the answer is no, that's something different. But that was a very good question. Like that was an interesting question. I definitely like that's why it like kind of like stuck out to me. So but I think just more atmosphere and like the Earth's distance from the sun or something like that, I think.
Yeah, great question.
Many lifetimes to complete, even at their fastest. This would be slow enough that we could come to terms with our new reality. If our satellites don't have enough shielding, we would have time to build some that were better protected. If solar radiation becomes a larger risk, we could remain indoors more. Sun cream might become more powerful to mitigate the dangers of cancers, if not remove them entirely. And according to NASA, even if our field were to significantly weaken, it's not like we would be left without protection. Our atmosphere itself can catch radiation, meaning that we would remain safe from solar winds and cosmic radiation, at least to some degree.
Oh,
It would
that's
take
the Aurora
far longer than
Borealis.
10,000 years for our atmosphere's ozone to be stripped away. But I would be surprised if there wasn't at least some turmoil, at least while we adjusted to living under a reduced magnetic field. Big changes to how a society operates are always painful. And this isn't entirely hypothetical. Did you know the Earth's magnetic field has been steadily weakening for the last 200 years? It would take another 1,300 years for it to vanish completely, so there's plenty of time for it to stop its current downward trend, and there's no reason to think this isn't just a temporary wobble. But on top of that, there is also the South Atlantic anomaly to consider, a section of the Earth's magnetic field that is already showing signs of significant weakening that covers most of the space around South America and the neighboring ocean. This zone might not influence life on the ground, but is dangerous enough that it has fried satellites and threatened astronauts. The Hubble telescope has to turn itself off every time it flies through it. Imagine that, but across the entire globe. That's why.
So the reason it has to turn off is because of that increase in radiation exposure over this specific region. So that's why like it does have an effect over satellites passing through this region.
What we might expect while the poles are reversing. Concerningly, the South Atlantic anomaly has been growing continuously since we started keeping track of it, possibly suggesting the approach of either another geomagnetic wobble like the Deschamps event, or that a full-blown reversal is already upon us. If it happens, it won't likely be something that ends civilization as we know it. But if the study about Australian megafauna is correct, it isn't going to be without impact either. Species could die. Humans will have to accommodate a very different, more hazardous space environment. It's interesting to learn about geomagnetic reversals and their potential impacts on the planet. But while we are not likely to see one happen in our lifetimes, for the generations of humanity after us, this might turn out to be a lot less hypothetical. They might be seeing it firsthand. Scientists spend a lot of time and resources trying to check on the health and well-being of our Earth's magnetic field, for good reason. And yet, on a day-to-day level, in all the hectic rush of living, we sometimes forget to spend time and effort checking in on our own mental well-being. Talking to someone is one of the most important things you can do for yourself.
It's so awesome how like these videos just like include an ad in there. Like you think it's part of the video.
I know.
Like,
So I believe that's it for that video. But
okay, that's it. All right.
But you know, essentially, like all to say, Goldie, it's not going to be like a terribly catastrophic event if and when the pole reversal happens. Like we would be able to adapt. We would just have to make some adjustments, like our technology would have to be improved and updated. There could be some unfortunate like extinctions for animals, because for them it could be a little bit harder to adapt, especially for things like confusion during migration and things like that as well. But we did also have that episode a couple weeks ago about wolves to dogs, and how we could potentially bring back some.
I was actually just thinking about that, and the dire wolves, and how they're bringing them back from extinction. So yeah, like we have the technology to if that was going to happen, we could help the animals.
Exactly. So there's definitely things that can be done if and when that happens. So yeah, that was magnets, Goldie. Wow. And what would happen, if Earth loses its magnetic field, which isn't likely to happen anytime soon, but something like a pole reversal or any sort of shift like that is more likely.
Yeah, and it's already happening because there's like a giant hole in South America. So now, like, new fear unlocked. Thank you.
Too funny. Okay, did you have that video, or should we go to?
Yeah. So, guys, this is like probably the most accurate depiction of like you know how like it's like super random how like the magnetic poles can just flip randomly. So here's a very good video to show like how this flip of like magnetic north and south can happen just like super randomly, right? So here you go. This is on the official Global News channel. So like Global News uploaded this video and did the edit and everything as well. So it's so good. But yeah, guys, so listen, that's how quick the magnetic fields can shift, right? One day you're on one side, and then the next day, boom, you're flipped around. So
Oh my goodness.
there you go.
Um,
But did you want to go to maybe the super chats and the questions?
Let's go to the super chats. Okay, so thank you guys for sending over your questions and your comments. So we'll be going through those now. And I actually do want to mention, I haven't seen them tonight, but I do want to give a shout out to a subscriber / member called Seeker of the Way. So if you watch this later, thank you. And the reason is because I actually changed the name of our membership group to Gamma Rangers from Gamma Squad, because Seeker of the Way in our last live stream coined the term, and I absolutely loved it. So I submitted a change request to YouTube, and so now all of our members are Seeker of the Way. So yeah, welcome to, all the members are Gamma Rangers.
I love that.
Anyway,
go Gamma Rangers.
Yeah, I love it. So I've got some fun ideas also coming up for all of our Gamma Rangers. I made a post a couple days ago to ask what people were interested in seeing in terms of exclusive content. So I'll be working on that over the next little bit. Meanwhile, enjoy all the fun badges and emojis. Hopefully, if you have any specific requests for any emojis that you want, let me know. And yeah, we're gonna have some fun with that. But let's go to our super chats. And our very first one is from Goldie. Goldie, thank you so much for the super chat. You know, you don't have to.
Magnets! Yeah. We're learning about magnets. I was just excited.
Clearly. Thank you. I appreciate that. And yeah, magnets. Tell me one thing that you learned about magnets tonight, Goldie.
Magnets, if we don't have magnets, we can die. Magnets keep us alive. Magnetism keeps us alive.
Magnetism keeps us alive. Okay.
No, but actually, like, you know, more practical. One of the things that I learned about magnets is that the reason that magnets work is because, you know, in like a random object, let's say like my can of bubbly, the electrons are pointing in all different directions. But in a magnet, they're pointing all in one direction, either up or down, and then that, makes it magnetic, whether it's north or south.
Yeah, great. But your can of bubbly is probably not a ferrous material.
It's aluminum. It's aluminum. I know. Okay, yeah. Iron. I don't know, man.
Yes, in theory, yes.
Wait, paper or paper clips iron or aluminum?
They're
not. They're definitely not iron. They're probably aluminum. Okay, but assuming if this was a ferrous material.
No, but paper clips are magnetic. Because I do know, like, you can hold a magnet to a paper. But do you have a magnet?
Yeah, I have one on my fridge. Let me go. You know what? Let me go grab my fridge magnet. No. Now you put me on the spot. I'm gonna go grab my fridge magnet.
Okay, I'll go through some of the comments.
Do you have to wait until I come back?
Oh, okay. I have to wait. Okay. Well, guys, How about? Oh, she's still talking. Okay.
You like my fridge magnet? So this is my fridge magnet. It's a handmade gift.
Oh, I love that.
Someone gave it to me, and then this is the magnet on the back. So what I learned is that the reason that this magnet is the way it is because all of the electrons are pointing in one way, and that's what makes it stick to the fridge.
So did you stick your clip to it?
No. Oh my gosh! It's stick! Yeah. Well, how do I do this?
Wow.
It's magic.
Magic. Also, you're doing demos too. It's not just me.
Look at that.
I love it. So
I'm
yeah.
rich. Look, I should get like my Hogwarts thing now.
Okay, so Francis Conti says paper clips are ferrous because soft steel is springy and ductile. Okay, so I guess it's made of soft steel. Thank you so much, Francis, for sharing that. But
guys, I can take over the GammaRay Report. Look, I can do demos too. Look, guys. It's magnets.
Oh gosh, that's funny. Okay. So going to the next super chat. So we have Tread that says, Goldie, you need my kind of hat. Okay, Goldie, I think you got to get a hat like Tread. What is that? Does that look like a top hat, kind of? Tread,
maybe a top hat. I kind of like my hat though, Tread. I don't know. Is that a fedora? Fedoras don't look good on me, but I'll think about it.
It's kind of small. I can't tell, but it could be a fedora. Tread, tell us what kind of hat you got.
Yeah, your hat definitely suits you. It looks good on you. I don't know if it would look good on me.
I think you could pull off a fedora, Goldie.
I'll think about it.
Okay, so this was a comment that you starred, Goldie, by Rob, who's asking, how far can gravity affect something? Ooh, that's a great question.
So I know this because you were kind of speaking about gravity and magnetism, like during the four forces that you were speaking about. I don't know if it's something you can answer today, but I think it was a cool question, and I think that maybe you could do either a video or a live stream on gravity.
Oh, sorry. Sorry, Goldie. Yes, on gravity. I think that's an excellent idea. But I can give like a high level answer right now. But I
think a live stream on gravity would be pretty cool as well.
Yeah. Okay. But I guess to answer this question for now, like essentially gravity can have like an infinite range. So like in principle, every object with mass in the universe exerts some sort of gravitational pull on every other object, no matter how far apart they are. But it's essentially, I guess it depends on how massive an object is and whether the mass is actually exerting any sort of noticeable force on the other object. So like, for example, Goldie, when I'm standing next to you, we're not going to feel any sort of like gravitational forces between each other because we're not.
I do, because I love you, and whenever I see you, I'm just attracted to you, and I want to give you a big hug.
That's so funny.
That's the magnetism.
For anyone in the chat, this is a great time to like make any yo mama jokes. Like, yo, so fat, I can feel her gravitational force, time for that kind of humor. But yeah, essentially, like in practice, gravity from very distant objects becomes so weak that it's overwhelmed by closer, more massive objects. But essentially, the range can theoretically be infinite. But yeah, I think I can definitely do a segment on gravity later on. Okay. So Minor Dine says this training aid for sure needs to be on a merch store before the school year starts. Oh, that's so kind of you to say.
Yeah, Minor was referring to the graph with the four like fundamental forces.
Oh, yeah, that is simple enough. I want to say for like elementary.
You get this comment like every live stream. You really need to start a merch store where you can sell your posters, because I think people would be interested in getting copies of your posters.
I'll get started on that. I've been focusing more on like actually creating like the content and the videos, but I can work on that too. Thank you for that, Minor. So next we have this other starred comment that you starred, Goldie, from Canoe Crab, that says, I like how you explain it so clearly and with passion. That's so kind of you to say. Thank you, Canoe Crab. I mean, I have spent the last couple of days just like learning about magnets. So like it's been fun, like learning about topics and like coming and explaining it to you guys. It's been part of this process, and you gotta enjoy the process to be able to come and be excited about sharing it. And I think like what gets me really excited about it is like when people actually start to understand what I'm saying. That like feedback loop gets me excited and makes me want to keep going. So thank you so much for sharing that. Next we have Tread with another comment. I get lost at quantum physics. God wouldn't. Yeah, quantum physics, it's a tough one, I gotta say. Like, I think like I don't know how I can do like a good live stream on quantum mechanics right now. Like, I think I would definitely have to do it in different segments and start from like the fundamentals and then kind of work our way up, because it's like a completely different universe, Goldie. Like, it's so strange and it's so weird, and like the laws of physics that govern the quantum scale are completely different from the laws of physics that govern like our regular scale.
Yeah, that's what I've heard. Like that's pretty much the only thing I remember from like quantum physics is like the smaller you go, the less like the standard or accepted laws of physics apply. So that's like, kind of gets to like Schrodinger's cat or whatever, right? Like it's like the smaller you go, the rules don't apply. And then especially when you get into like subatomic particles like quarks or whatever, it's like a whole other like set of rules. It's like a whole other universe or something, which is really interesting. But I mean, that's so super complicated. Like I don't think you could do or explain all of that in one live stream.
No.
Yeah, but again, like I think what's really fantastic about your channel is that you're able to take these very complicated concepts and break it down so that the rest of us can understand. And I think like that's what we appreciate about you and being here, right? It's like you're able to like explain it to the rest of us, right? Like you explain it to us commoners, right?
You're so funny. But yeah, I mean, like quantum physics and quantum mechanics is like a whole branch of physics. Like
Yeah.
you definitely can't do it in one go. And like, yeah, it'll be interesting to get into that. But like we've been kind of picking at it here and there slowly. I mean, we talked about quarks today briefly. So, and
I feel like you're building us up to that. So like a year from now, we'll be experienced enough to get to like quantum physics, right?
Okay, next comment is from Bob Mander that says, FYI, it's difficult to see the very bottom of the chart with the banner scrolling by. Yeah, thank you for sharing that. I did notice that it might be difficult to see that. So I'll be more mindful of that moving forward, to remove the scrolling banner while I'm sharing the diagrams.
So one thing I want to comment, I believe, if I'm not mistaken, so in this view, like the regular view,
Yeah.
The banner hides the bottom. But if I recall, I feel like in this view, the banner doesn't hide it. So play around with that. But I mean, yeah, like if you're finding that the bottom is not showing, then yeah, for sure you should, you could remove the banner temporarily.
Okay.
But that's
Perfect.
a great comment. Thank you, Bob.
Thank you, Bob. And thanks for the super chat. So next we have a start comment from Gerald, who says, my 10-year-old would love this stream. Oh, that's so great to hear. Yeah, let's get those 10-year-olds learning about science. I love it. I love that. Tell him to share with his friends. They could have a watch party. Okay, next we have Gobadon, who says, I heard gravity is caused by massive objects curving the space around them, but why do we accelerate when we fall? Oh, I'm loving all these gravity questions. Okay, so Einstein's view of gravity is that you're not necessarily being pulled downwards, but you're accelerating because you're following the straightest possible path through that curved space-time. So according to the theory of general relativity, mass and energy curve the fabric of space-time around them, and then objects that are moving through that curved space-time are naturally following these paths, which are essentially the closest thing to a straight line within a curved universe. So if you think about, like, let's say you like jump off a building, you're actually in free fall and you're following one of these natural paths. So sorry, instead of jump off a building, let's go with like jump out of a plane, skydiving. Makes it less morbid. So let's say you're skydiving, you jump out of a plane, you're in free fall, and you're following one of those natural paths. And the reason you appear to accelerate towards Earth is because the geometry of space-time near Earth causes it to kind of converge towards the planet. So I hope that explains it. But yeah.
I feel like one of your future videos or live streams should be about gravity, because that would be kind of cool.
Yeah. Gravity. Okay. So next we have Canoe Crab from New Zealand, I think. Is that where and Zed is from? Awesome. Love to have someone from New Zealand. So they say, thanks, Rose. I've been studying quantum computing, just a beginner, and never understood how spin was measured. Oh, that's so interesting. Quantum
So
computing is
basically,
a fascinating topic.
Can I just say something? So this just goes to show how great you are at explaining things, right? So like this super chat came when you were explaining about the spin and what, like your graph with the spin stuff. So very, very cool.
This is, I love comments like this. This just validates me. So thank you so much. Thank you for that. Next we have Pious Vapor, who says, not to understate the educational value of your channel, but you all are quite entertaining and fun.
Thank you.
I would say we're a fun bunch. We got some humor, we got some jokes here and there. Might be nerdy sometimes, but we're here. We're having fun. Thanks for the comment. Next we have Spaghetti, who says magnet lives matter. Yes.
This is a pro magnet channel. No magnet deniers allowed.
And then we have a start comment from Bob, who says, are you going to be covering refrigerator magnets? I didn't go too far. You know what? Goldie got it. This is the extent of our fridge magnet commentary tonight.
There we go, guys.
Like a live demo. Wow.
Live demo right here. Whoop. There we go. Fridge magnets.
Love the sound effect. It comes with a boop and everything. That's excellent. Okay. And then we have Raider with a super sticker. Thank you, Raider, for
so great to see Raider. Rose. So this is really interesting because Raider, like when I first started my channel like 6, 7 months ago, and I would do live streams in the evening, Raider would just show up and support my channel by giving me like a super sticker. And Raider, yeah, like Raider has never commented nothing, but like every once in a while they've shown up on my live streams and given me a super sticker. So I just thought it was so cool to see Raider now on your channel supporting you as well. So Raider, whoever you are, thank you so much for supporting my sister's channel. This is just super cool to see Raider here, because Raider is one of the OG supporters of my channel back when I only had like 1,000, 2,000 followers.
Wow. Well, so nice to have you, Raider. Thank you so much for your support and for being here and having fun with us, learning about science. Next, we have John Diamond with a super sticker. Thank you so much, John, for the support. And then we have John with a comment. Rose is starting to explain the dancing Wu Li masters. Love your content. Hi, Goldie. Ooh, okay. So I've heard about this book. I haven't read it, but let me
pull it up. Let's see, because I'm curious to know what this is all about.
Okay.
Could be something to look into as well, for me anyway.
Okay, let me go to Okay, so Dancing Wu Li Masters is a 1979 book by Gary Zukov, a popular science work exploring modern physics and quantum phenomena in particular.
So this super chat came when you were explaining quantum physics and quantum mechanics to us.
Oh, nice. Okay, I gotta check out this book. I haven't read this, but I would love to read it. Oh, 1979. Goldie, do you think it's a conspiracy?
Oh. I'm trying. I've been so good at avoiding politics.
I'm joking.
So now you're tempting me.
I'm sorry. No. Yeah. Good. Thank you so much for the comment and for sharing that, John.
It's such an amazing compliment, because like I think people are just really appreciating how you're able to break down these very difficult concepts and like explain it in like a way that the rest of us can understand. So thank you so much for that, Rose.
Of course, thank you. Thank you for the comment and for that lovely compliment. So next we have Fleshy Interloper with a question. Do solar winds reach Mars? Ooh, that's an excellent question. And yeah, absolutely. Solar winds can reach Mars. And because Mars no longer has that strong global magnetic field, it is much, much more exposed to solar winds than Earth is. And like the constant stream of solar winds that is reaching Mars is certainly contributing to like the desert terrain that that exists there today. Because when it did have the global magnetic field, it was being protected by a lot of that solar wind. But now, because it's lost it, and over billions and billions of years, it's kind of transformed into what it is today. And that's primarily because of things like solar winds, which have stripped away a significant fraction of its atmosphere, helping it to develop into that red planet. Great question. Next, we have a start question from Canny. It says, do we use magnetism? Canny, yes, we do use magnetism. And, I actually had a final diagram, which I didn't end up showing, but I'm going to pull it up real quick. I'm not going to go through the whole thing, but I'll go over a small section of it, which covers a little bit around how magnets are powering modern civilization today.
So this question, Kenny asked this question when you were talking about how various animals like birds and butterflies and turtles use magnetism. So that's where the question came from, is like, do we use magnetism?
Yes, yeah, absolutely. And so
No, but I think it was like innately, like not do we use magnetism through technology, but do humans innately use magnetism the way like birds do?
Okay, I understand now. Sorry,
Yeah.
this is a question, but I want to say no. I don't think humans have the same physical capabilities that animals do when it comes to like being able to use magnetism. And so I think like scientists actually, and if there are any animal experts in the chat who want to chime in here, let me know. But I think like scientists still aren't exactly sure how some animals actually are able to use magnetism to help them through things like determining direction and like location and things like that. But like birds, for example, use Earth's magnetic field to help navigate during long migrations spanning thousands and thousands of kilometers. And like the sea turtles, now I can't stop thinking about the kid. But sea turtles also use magnetic cues to find their ways across ocean floors and like even return to like beaches where they were born. Salmon use magnetic information to kind of help locate their home rivers and like after being years and years at sea. And like some insects like the butterflies also use the magnetic field during migration. But like scientists are still trying to understand how this actually works. But like some scientists think that like maybe some animals can detect magnetism through like specialized molecules in their eyes or in their bodies that kind of help them be more in tune with the magnetic field of the earth. I don't think humans have this characteristic. And
Yeah, I don't think we do, because if we did, we wouldn't need to develop all this technology that you're showing on the screen right now, right? Like there's only one human that I know of that actually like has the inherent power to use magnets.
is this a joke? Who is it?
Magneto.
The X-Men? That's so funny.
I mean, no other human like can use magnets as like a superpower, right? It's only Magneto. So
yeah.
I mean, given the fact that Magneto is an X-Men, that kind of makes me think that we humans don't have an innate power to use magnets. Because if we did, Magneto wouldn't be an X-Men. So.
I guess not. I guess not. But anyways, I guess since I'm showing this diagram now, again, I'm not going to go over it all, but like magnets today, these are some functions that humans use, magnets, in a variety of these different devices. And like definitely like every day, we're all using magnets all the time. Thank you so much for that question. Old Blindly says Rose is always writer. Thanks.
I agree. Especially when we're on a class field trip into Spaceland on the GammaRay Report, Science Land, yeah.
And then we have a start comment from Daniel, who is asking, "Can we terraform Mars?" Ooh, Goldie, you started this one. You wanna learn about terraforming Mars, eh?
Yeah, isn't like Elon Musk working on something like terraforming? I don't know.
I think that could be one of his eventual goals, but like in theory, yes, like Mars can certainly be terraformed. With our current technology today, it would be like an extraordinary feat, very expensive, very difficult, and could take quite a long time for it to happen. But like you got to start somewhere, and like someone like Elon Musk can certainly be one of those people who kind of starts to think and actually put the practical steps towards something that would work towards terraforming Mars. But like ultimately, we would need to make it warmer. We would need to create a thicker atmosphere. We would need to provide stable water, stable liquid water specifically on the surface. And one of the challenges today is that Mars has very atmosphere to work with. And there might not be enough carbon dioxide within the planet right now to create an Earth-like atmosphere. And like another problem is that it lacks that global magnetic field. So then you have things like the solar winds continue.
I was just gonna say, now that like you've taught me about this, I could say, well, how could we if there's no magnetic field? Because we rely on the magnetic field to protect us from catastrophic incidents like the solar winds, right? So
yeah, so I mean, like you would have to consider like creating some sort of artificial magnetic field for something like that, and like even that, like we certainly don't have the technology today to build something like that. Like it would certainly be very expensive.
I mean that we know of.
Exactly. Yeah, that we know of. We don't know what happens, in the dungeons.
And Area 51, we have no idea what goes on in Area.
We don't know, but theoretically, yeah, possible. Next we have Newton 11 with a starred comment this week on How Do We Die with Rose and Goldie. Maybe I gotta rebrand. I gotta rebrand the show.
But I do want you to do a show on cordyceps though.
I think that'll be quite fun, but I imagine for the whole show you're just gonna be like that'll just be your face the whole time. I'm pretty sure.
Oh gosh.
Which brings us to the next super chat from Minor, who says, Rose, you seem to like scaring your sister, don't you? I mean, it's part of my job. I think it's part of the contract that I signed when I joined this earth. It was like,
when you were adopted?
When I was adopted.
I'm teasing. She wasn't actually adopted. And by the way, there's absolutely nothing wrong with adoption. Like that's nothing to do with that whatsoever. It's just how I would, tease my sister and make her cry. It's like, when I would basically, like when I was younger, I would look at her and I would be like, hey Rose, do you want blue headgear or pink headgear? And then she would just cry.
Would burst out crying, yeah.
The concept of headgear would like
traumatic.
Even though like headgear is an amazing thing because it fixes people's faces, right? But that's just me as an older sibling bullying her.
I think we've moved beyond headgear technology. I don't really see many people.
We've moved beyond that technology for sure.
Next we have a comment from Fizz Engicist who says super volcanoes. That would be another fun next topic. But again,
how do we die? Like, you know what? Super volcanoes. You could talk about Pompeii. Visited Pompeii.
We did. I think the only like nice stream I've had was maybe like the wolf to dog one that wasn't about dying.
And Pluto.
Yeah, and Pluto. Okay, so I guess people have like some sort of morbid curiosity, maybe, but who knows?
It is cool. It's interesting.
Yeah. Thanks for the comment, Fizenge. Next we have WMK who says Poyanda magnets. Yes, Poyanda magnets. Billy Cunningham who says magnet truther movement.
We are pro magnets here.
That's so funny.
Magnet deniers are not allowed. Guys, anyone who like denies magnets, just ban them.
Next we have Tread who says, after this talk, I'm going back into my tree. Well, Tread, that sounds very cozy. I hope it's a nice tree with everything you need. Next we have Daniel who says, you can't go on a zombie tangent, then expect me to not think about zombies. I blame you for this, Goldie. I blame you. The scary thing about the cordyceps, though, is that like
it could happen. They could evolve. It could happen.
It's happening to ants and like insects.
Yeah, I know, because I've seen it, and I'm like, that's why it could happen to us too.
Next, we have a start comment from Stuart who says, I love this show. Thank you so much, Stuart. Thank you so much for being here and for spending your time with us. A comment from visitor Clockin10 who says, suggested topic, zombie emoji. Science of a zombie apocalypse. Ooh, okay. That would be interesting. So I think that would have to have a lot of like theoretical what ifs.
Well, it kind of goes into the whole cordyceps concept, right? Like, what would a zombie apocalypse look like? And I think like the cordyceps thing is probably
yeah. But you know, like in all of the zombie shows I've ever watched, Goldie, like the scariest thing is always the other humans. Like the initial shock is like the zombies, but then the most dangerous thing always just happens to be like the other humans that you're like battling with and like trying to live with in the same planet. But you know, that's a question about human nature.
Yeah.
Next, we have Spaghetti with a super chat. Rose, do Kardashev scale and Dyson spheres next. Ooh, okay, interesting, exciting topics. You know, maybe a bit after the cordyceps one, but I will write these down and stay tuned. Next, we have Old Blindly, who says, has Rose been bought by Big Magnet?
Yes. Honestly, I thought that comment was too funny not to star and highlight. I just thought it was too funny.
Thanks for that. You know, I can't say. Like, if I have, I cannot confirm nor deny. So, you know, we'll just say no for now to be safe.
Deny.
Yeah.
You know what? You're spinning the answer like a magnet.
Yes. Okay, so next we have Roman Viking with a question. Can we artificially create a Mars magnetic field? Oh, interesting. Yeah. And so I think this is part of the considerations that we would need to have for terraforming Mars, but like it would be one of the largest engineering projects humanity has ever attempted. Like think like Death Star level of like engineering that would go, okay, maybe not that big. I don't know, or maybe it is that big. Anyways, large scale engineering project that we would ever kind of have to attempt because Mars no longer has its global magnetic field. Theoretically, yes, like we could create an artificial magnetic field for it, but it would take a lot of resources, energy, time, massive engineering feat. It would take years and years. So theoretically, yes, probably not something that's going to be done anytime soon. Next, we have Amir, who gifted a GammaRay Report membership. Okay, so we got a new Gamma Ranger. Welcome to the Gamma Rangers.
And thank you, Amir, for gifting a membership.
Yes, thank you so much, Amir, for gifting a membership. And next we have Tread with a super chat. 20-ounce coffee mugs would be great. Okay, yeah, I think I need to
diagrams. Yeah, we need to work on your merch store. Don't worry, guys, we'll figure it out.
Yeah. And I need to pick, because I have quite a few diagrams now. I think I need to pick like some of the more popular ones and see like which ones people would be interested in. Next we have another super chat from Tread, who says, look up to the sky and smile back. Peace sign. I love it. Lovely comment, Tread. Thank you. And Tread, who gifted another membership. Thank you so much, Tread, for welcoming another Gamma Ranger to the crew. We're so lucky to have you join us. Next, we have a novel
Odyssey.
Oh, Goldie, sorry, before I get to that, have you heard of the new Odyssey?
I've heard they've like totally like ruined it, and yeah, Helena Troy her face does not look like the face that would sail 1,000 ships or something.
Oh,
I don't
really?
know the drama of that, but
oh no. Okay, I don't know too much about that yet, but I've always been fascinated with Greek mythology and all of that, so I'm very excited to go see it, but I don't know too much about that controversy. I actually don't know.
Oh, so what is it that you were gonna ask?
I just wanted to see if you wanted to go see it with me.
I would, yeah, I mean, sure. I mean, I've seen the original like Odyssey movie that came out like I think 15, 20 years ago or something, and that Odyssey was phenomenal. It was so good.
Oh, really? I don't think I've actually seen that, so maybe
You
I need to
probably
check it out.
saw it, but you were just maybe too young to remember or something.
Maybe. But okay, so a novel Odyssey is asking, do sunspots have an effect on Earth's climate? Ooh, okay. So sunspots are linked to the sun's activity, which can affect Earth's climate slightly, but it's not the primary driver of things like modern climate change. So like these sunspots are essentially these darker regions on the sun that are caused by intense magnetic activity. And what's interesting is that when there are more sunspots, the sun is actually slightly more energetic overall because sunspots are accompanied by these other brighter regions. And so, like, sometimes these changes can cause these small variations in the amount of solar energy that reaches Earth, which can have some subtle effects on climate patterns. So, I want to say, like, somewhat, like minimally, but not like in any sort of large way that we might be anticipating. And then last but certainly not least, we have a, oh look, it's a paper clip. Clippy, yeah.
It's Clippy. Oh my gosh, that gives me like memories of like, Microsoft when they had like Clippy the paper.
Yeah. So TFDX with a super chat that says Mighty Morphin Gamma Rangers. I love that. Thank you so much. Thank you so much for the super chats. Thank you so much for the super stickers, the membership gifts. It was so nice to have you all here with us tonight. I hope you guys all learned something new. Hopefully you're walking away tonight with a little bit more knowledge, and maybe you can go show off a bit to your friends with some fun facts. And Goldie, thank you so much for tuning in as well and asking questions. And it's always nice to have you here. I'm very excited to watch more of you this coming week. And yeah, I'm also excited to start working on cordyceps.
Yay! So guys, no, it was so fantastic to be here. Like this was actually a lot of fun and it was super cool like learning about magnets. Like you would think it's a simple topic because magnets play such like just they play an important role in our daily lives, but we don't really think about it too much. But like you broke it down and it was super interesting, and now I basically know that like we literally rely on magnetism to survive.
Yeah.
So I'm excited for your next live stream.
I'm excited too. So we have a question in the chat from Ed Warren who says, is this a typical show? I want to say, yeah, my live streams are pretty typical to what tonight was. We normally pick a topic, we go over some of the concepts behind it, we watch some videos that kind of go over some of those concepts, we ask some questions, and we have some fun.
Yeah, and it happens every Sunday evening, every Sunday at 7 p.m. Eastern time.
Yeah. So yeah, if you like it, amazing. We'll be happy to have you back.
So I'm gonna say goodbye to everyone, but of course, before Rose, you end the live stream, you're gonna have to, land the plane. But for everyone who's watching, before Rose ends the show, I'm gonna head out. So I just want to say, thank you, everyone. Rose, such a pleasure to be here. I really enjoyed the live stream, and I cannot wait for your next live stream. So everyone who's watching, make sure that you like and subscribe and turn on your notifications so that we can all learn more about science. So Rose, thank you so much. Have a great evening. And guys, everyone, I'll see you all tomorrow. Same time, same place, same channel, The Goldie Show, for day 177 of Iran Revolution Live. See you guys all.
Thank you, Goldie. Looking forward to that. And guys, put on your seatbelt because we are hopping on our Q400, coming back from Planet Magnet Land, I think it was. And we're coming back down to Earth. And see you all next time.